Yes, sir.
Okay. So let us begin our discussion from the point. Okay. Right. Okay. So so I will just rediscuss a couple of points. Right. Wait. Okay. Okay. So let me wait for another 2 minutes. Okay. Otherwise, I will start again and I have to stop. So hope everyone can see the slide. Hello.
Yes, sir. Yes, sir.
Okay. Okay. So let us begin from the point where we have left in the last class. So I was discussing about the space-time four vector and the Minkowski diagram. So I should tell you that this geometrical interpretation of Lorentz transformation in relativity was basically due to this Hermann Minkowski, an Austrian physicist, who first proposed this kind of visualization of Lorentz transformation and interpretation of different consequences of relativity. So we already have discussed about this, that the space and time, they constitute a four-dimensional continuum, which is hyperbolic in nature. It's not Euclidean, and we can denote the four components of space-time four vector as x0, x1, x2, and x3. And when we try to relate this space-time component between two inertial frames, then we have the set of Lorentz transformation is shown here. Okay, so here I have used x0 and x0 prime to denote the relationship between ct and ct prime. Similarly, x1 prime is nothing but x, x2 prime is nothing but y prime, and x3 prime is nothing but z prime. So these are the same transformation that we have learned earlier. Now, what I was trying to show you, that Lorentz transformation is nothing but a hyperbolic rotation of Minkowski space. And to explain that, here I have shown you the space-time axis in the unprimed frame, that is the S frame. So this vertical vertical lines are, this is the space axis and this is the time axis in the unprimed frame. And here I have drawn two sets of hyperbola, which basically shows you the lines corresponding to c square t square minus x square equal to 1 and x square minus c square t square equal to 1. That is, you can have a bunch of hyperbola with different values on the right hand side. I can take a hyperbola with x square minus c square t square equal to 2 or 3 or 4, anything, but this is a special hyperbola used for calibration, because you see here, if I see this space time interval is 1, right, x square minus c square t square equal to 1, and we want to first find out the unit space interval and unit time interval in the primed and unprimed frame, because that is very important when we talk about measurement of time interval or space interval. So if you consider this hyperbola to be x square minus c square t square equal to 1 or x1 square minus x0 square equal to 1, then you see this coordinate of this point r, because this is the space axis in the unprimed frame. So x1 equal to x here and x0 equal to 0. So time is 0 here. So if you put time equal to 0, this is nothing but x equal to 1. That means in that unprimed frame, the distance from origin to r is nothing but 1 unit of space. And similarly, if you go along the upper branch of the hyperbola, here if I consider this point S, you see the equation of the hyperbola is c square t square minus x square equal to 1. And this is the time axis. So space part is 0, x1 equal to 0 along this line. So if you put x equal to 0 here, you get ct equal to 1 or x0 equal to 1. So distance from origin to S is nothing but 1 unit of time in the unprimed frame. And we want to see what are the space-time axes in the primed frame. So to get that, we have to understand when we apply Lorentz transformation, these are the Lorentz transformation, you see. So what is x0 prime? You see, x0 prime is nothing but the time in the prime frame, new frame. x1 prime is nothing but the space axis, that is x axis in the prime frame. So similar to x1 equal to x, you see, we will have x1 prime equal to x prime, or x0 prime equal to 0. That will be the space axis in the prime frame, similar to the same. So if I put x0 prime equal to 0 in this equation, to get the space axis in the prime frame, I have to put x0 prime equal to 0. And if I put x0 equal to x0 prime equal to 0, we get x0 equal to beta x1. This is the first one, right? And if you get x0 and x1, so this is your x1, this is your x0. So ratio of x0 and x1, that is the beta, and that is nothing but this angle, tan of the angle of this angle, right? So tan alpha equal to beta, so alpha equal to tan inverse beta. In the same way, if you go to this axis, again you see this your new time axis will be x1 prime equal to 0. So along the new time axis, space should be 0. So x1 prime equal to 0. So if you put x1 prime equal to 0, that is the second equation, you get x1 equal to beta x0. So here it is not x0 equal to beta x1 but x0 equal to 1 by beta into x1. But again, if you see this is x0, along this is x0, this is x1. So if you take the ratio between x1 and x0, that will be again tan of this angle alpha, right? Because here, see the direction has changed. This is your x1, this is x0. In this case, this was your x1, this was x0. So that's why this thing fits perfectly, right? So alpha, tan of alpha will be again beta. So alpha equal to tan inverse beta. That means when you apply a Lorentz boost, your space-time axis in the new frame will be non-orthogonal. In the unprimed frame, it is orthogonal. You see, x and ct are perpendicular to each other. But when you jump to a new inertial frame, which is moving with velocity v along the x-axis, your space-time axis is non-orthogonal with respect to the unprimed. Yes? Any question? Someone trying to ask something? Okay. So this set of axis, the new set of axis here drawn here, x1 prime and x0 prime are the space-time axis in the prime frame. And here we see that the angles are same. You see, this is rotated by alpha, this is also rotated by alpha. But here is an important difference. When we saw the example of rotation in Euclidean geometry, whenever we applied a rotation to the frame of reference, both the axis, space axis and time axis, or the two space axis, like this example, when I showed you here, you see this is x, this is y. When we apply rotation, both rotates by an angle theta along the same direction. But here you see it opposite, right? X is moving x0 prime is moving counterclockwise, while x0 prime is moving along the clockwise direction. So why that case? That is the region behind that is hidden inside the Lorentz transformation, right? If you look carefully, you will see that instead of minus, right, since there is a minus sign, suppose you assume for the time being that this time axis is rotated along this direction. So it will cut the upper branch of hyperbola somewhere here. But this set of transformation is not going to change. If you have two inertial frame, one is at rest, another is moving along the x direction with the velocity v, this is a unique set of transformation which is not going to change. But this is telling you x0 equal to beta x1 along x0 prime equal to 0, right? So in that case, you see clearly from this equation, this has to be negative, right? But this is positive. Right. So when will the time axis will tilt along this direction? When? Well, it will happen. When it will happen? Suppose the prime frame is moving along the minus x-axis with velocity v. Then of course this will tilt along, the time axis will tilt along this direction, and the space axis will be this one, right? This one. the second quadrant. If the prime frame is moving along the minus x-axis with velocity v, then the space-time axis, which you are seeing the first quadrant with angle alpha, will come here in the second quadrant. Again, if you go to the prime frame, suppose the orthogonal coordinate is prime frame. So with respect to the prime frame, the unprime frame is already moving with velocity v along the minus x-axis. So if you take this orthogonal coordinate to be the space-time coordinate in the prime frame, then you will see that the space-time coordinate in the unprime coordinate is coming here, this one and that one. Again, those will be tilted by angle alpha. And third and fourth quadrant are nothing but the negative side of those space-time axis, right? If you extend this space axis along this will come here. Time axis will come here. Similarly, this one will be extended along the fourth quadrant, and time axis will be extended towards the fourth quadrant. So this is important. So I mean, you see, I already told you there are no special inertial frame. When you take two inertial frame, I mean, if you are observing the same event from two different inertial frame, the space-time intervals are not going to be same, simply because of the principle of relativity. So here, what I am trying to show you, that simply because of the transformation from an orthogonal to a non-orthogonal coordinate system, the unit of space and time gets changed. If you look at the 2 point P and Q, those are nothing but the unit time interval in the prime frame. Why? You see, this is x1 prime equal to 0. Sorry, x0 prime equal to 0. What does that mean? So if you take x0 prime equal to 0, that is nothing but the space axis, right? x1. Here I have written how to calculate the coordinates of point P and Q, where the non-orthogonal coordinate system cuts the two branch of the hyperbola. So here you see, I have already discussed this, but let me just re-emphasize the same point here. So x0 equal to beta gamma, we have already calculated these things, value of x0 and x1. So here for the s1 prime axis, x0 prime equal to 0, because that's the space axis. So x0 equal to beta x1 gamma. And since the equation of the hyperbola, this hyperbola is x1 square minus x0 square equal to 1. So if you put the value of x0, you get x1 equal to gamma. Right, x1 equal to gamma. So the intersection of this hyperbola and this straight line, which is nothing but the space axis, will give you the coordinate of this point P, which is gamma comma beta gamma. So gamma is the space coordinate of this point P, beta gamma is the time coordinate of the point P. Now you see earlier, so this is a unit interval in the prime axis, prime coordinate system. So in the unprime coordinate system, the distance from origin to R was 1. And now the distance from origin to P is gamma. So gamma is a number which is always greater than 1. That means your unit of length has changed. It has increased. So suppose someone with a scale. So suppose your 1 centimeter, here it is 2 centimeter. So if I ask you to measure 100 centimeter in this frame, and in that frame, the length of the here your 1 centimeter is 1 centimeter. So of course you will measure it is to be 100 centimeter. But here it is 2 centimeter is equal to 1 centimeter. Right? Don't get confused. It is just a unit of measurement which has changed. So the person who is resting in this frame, prime frame, he will find it to be 50 centimeter. So he will decide that okay, length has contracted, right? So it is see, length contraction and time dilation, which I think many people gets confused about, are symmetrical, right? No two frames are same. But again, there are this kind of confusion arise mainly because of the different kind of paradox discussed in different textbooks. Like if you for example take the twin paradox, right? It's asymmetrical. So age of one twin gets one person becomes older than the other. And why is that the case? If you really want to understand that, so here actually if you consider a twin paradox, see, length contraction and time dilation, I told you many times that these are interlinked. So if length get contracted, then of course from the other frame, the speed of light is constant in all frames. So if length gets contracted, of course the light will take smaller time to travel that distance. So L becomes L0. Sorry, L0 becomes L. So length has contracted. So naturally, if light takes a different time, so it will take shorter time. So time will definitely be different in that frame. So what I try to mean here is that length contraction and time dilation are two interlinked phenomena which is symmetrical. If you just take, for example, in this picture, some people have expressed doubt about this thing, like this time dilation thing. Here you see I have here shown you two clocks. One here, 1 here. But it is you may not get my point here, because at least you need a set of clocks which are synchronized. So suppose there are 10 clocks in this frame, and there is one clock here which is at rest. So if you compare the time of this clock with all the clocks which are synchronized in this frame, you will see that the clock here has become slow. Right. So again, if you take 10 clocks here and synchronize all of them with the clock which is in this frame, the observer in this frame will find that clock is going slow in this frame. So this is symmetrical. What I'm trying to say here in these two equations, both these are coming from the two different transformations. What I tried to show you that I have taken only one example where the clock is at rest in S frame. You can do it yourself. You can keep a clock here in rest and try to find out what the conclusion is. Here, since both the equations are obtained from two transformations, one is delta t prime and other is delta t. Here you see this one, delta t prime and delta t. Both are this is the inverse transformation of this one. So I should have the same conclusion. If conclusions are different, then it is meaningless. So that is what I tried to explain in this slide. Right? This is symmetrical. But again, if you want to understand the twin paradox, because there are hundreds of paradoxes in relativity, and if you want to understand the twin paradox, you have to clearly think about it. Because there are not only two frames, there are three frames. One frame is at rest. One frame is going to some another twin is using a spaceship to go to some other say planet or galaxy, wherever it goes, and then it comes back. So there is another third frame which is involved here. So the second twin, he switches frame from one to other. So there are three frames involved here. And if you want to understand this asymmetry, then you have to take into account this switching of frames as well. This paradox is very clearly explained in Reznick book, which I have suggested to you. If you are really interested about this asymmetry, there is a complete chapter on twin paradox, which shows and explains everything using space-time diagrams and also giving examples why the age of two twins gets changed, so why there is an asymmetry there. But here, when I'm talking to you about time dilation, I am talking about only two clocks, one clock here and one clock here, both are synchronized. One is moving with respect to other, right? So time dilation and length contraction in this case are symmetrical, right? So I am not going to discuss about twin paradox at this moment. Let me go back to the slide which we are discussing here. This is important because you see in the same fashion, if you look at the time axis, so OQ is now what? You see OQ is, what is that? What is the OQ gamma? So that unit of time has changed. So if you try to measure the same time with a different unit, your conclusion will be different. Your measurement will be different. It is bound to happen. And I should also tell you all the points on the hyperbola. This hyperbola is collection of points. So all these points are nothing but unit time measurement in the prime frame. Suppose I boost to another prime frame with a different velocity. So the time axis in that prime frame, suppose there is another frame S double prime, which is moving with a speed double than this speed. So the time axis in that frame will be inclined by a larger angle. Say here. Okay, so here. So it will cut somewhere here. So then this will be the new unit of time in that axis. You increase the speed, it will cut somewhere here. So that point will be the unit time in that prime frame. In the same fashion, if you increase the speed, your space axis will be also rotated by the same angle, and it will cut the hyperbola at different points. So all those points are nothing but the unit space interval. This hyperbola, the intersection of the space axis and the hyperbola, will represent the unit space interval in the prime frame. Similarly, intersection of this time axis and the upper branch of the hyperbola will be the new unit of time in the prime frame, right? Because it is the proper time which remains invariant. If you see this equation, c square t square minus x square, right? This is your space-time interval. I have taken it to be 1. Why? Because if I put x equal to 0, I get ct equal to 1. If I put equal to 2, that will be root of 2. Ct equal to root 2. So what I will do with the root 2? Because 1 is the unit of measurement. That's why I have taken it to be 1. You can take any other hyperbola. There is absolutely no problem with that. And what else I should mention here? So these 2 points are the unit of time, space and time in the prime frame. And you are measuring space and time in that frame using these units. So obviously your conclusion is going to be different than the person who is at rest in the S frame. Fine. And what else? So do you have any question on this? If you have any question, please ask. Can everyone hear me?
Yes, sir. Yes, sir. Go ahead.
Okay, okay, all right. So let me now just move into the next slide. So here you see this is not a dramatically new picture; it's the same picture here. But what I tried to emphasize is that you see how do I get the space and time coordinates? Given a coordinate system, what you do? So this is an orthogonal coordinate system, x0 and x1, right? This is a point P. Suppose this P represents an event in the space-time diagram. So I drop a perpendicular on the space axis, which is parallel to the time axis. It cuts somewhere here. So that's my space coordinate. Similarly, I drop a perpendicular on the time axis, keeping it parallel to the space axis. It cuts somewhere here. So CT is the time coordinate. So CT and X are the two numbers which are used to label the coordinates of P in the unprimed frame. And when we move to the prime frame, the space and time axis are now non-orthogonal. They are no longer orthogonal as in the unprimed frame. So in that case, see this, they are not orthogonal. So you have to draw this perpendicular which is parallel to the time axis, and definitely it will cut somewhere else, right? At x prime. Similarly, when you drop a, it's not a perpendicular, it's a line which is parallel to the space coordinate, it will cut somewhere here. So x prime and ct prime are the new space time coordinate in the prime frame. So that's why you are labeling the same events by different sets of number. But remember what I told you again and again, just like the length of a rod in 3 dimension, the space time intervals remains invariant. So although ct and x are different in different frame, so in this case it is ct, another frame ct prime, another frame ct double prime, and so on. But if you combine them, that is a space coordinate and time coordinate in a certain fashion, that is c square t square minus x square, or if you are using two events, then c square delta t square minus delta x square, that is absolutely invariant, low range invariant. Whichever frame you go, it remains invariant. And why this minus sign? That's because of the hyperbolic nature of space-time geometry, right? And actually you can understand all the consequences by using simply Minkowski diagram, like relativity of simultaneity, length contraction, time dilation. I have not discussed all of them because these things are very clearly discussed in this Reznick book. If you are really interested, you can go to the chapter and read those yourself. I will just discuss one of the important things, because length contraction and time dilation is nothing but the consequence of relativity of simultaneity. So if you understand this, you can easily understand the rest of the things. You see, so let us take two simultaneous event A and B in the unprimed frame. You can see A and B cuts the time axis at exactly the same point. So they are happening exactly at the same moment in the unprimed frame. But if I try to measure the two events in the prime frame, I have to draw two lines which are parallel to the x-axis in the non-orthogonal coordinate system. So draw two such lines. You see, these lines cut the time axis in the prime frame at two different points. So clearly, the event A and B are not simultaneous in the prime frame. If I take a opposite position where the two events C and D are parallel in the prime frame. So you see, when I draw a line which is parallel to the space axis in the prime frame, that line cuts the time axis in the prime frame at single point. So these two events C and D are simultaneous in the prime frame. But if I look at the two events from the unprimed frame, I have to draw two lines which are parallel to the space axis in the unprimed frame. So draw two such lines. You see, these two events cut the time axis in the unprimed frame at two different points. So clearly again, these two events which are simultaneous in the prime frame are not simultaneous in the unprimed frame. So clearly, I mean, the space and time are related in such a way that the space-time measurement are different in different inertial frame, and that is purely because of this relativity of simultaneity. Because you see, if you remember the essential points, when you measure time and measure space interval, how do you measure them? When you measure a length, you have to measure the reading at the two ends simultaneously, delta t equal to 0. But you jump to another frame, there will be a time lag between the two measurements, and that is the reason why your time is different, length is different. Similarly, when you measure time in one frame, your clock is at rest. So you are measuring time at the same location. There is no spatial interval. If you jump to a moving frame, you will see that when you measure time, interval, you are basically looking at the clock at two different places. So there is a spaced interval associated with the measurement in the time frame, and that gives you rise to the time dilation. So those the things you see in one frame, delta x equal to 0 and delta t equal to 0, in another frame it is not. So that means even in one frame it is simultaneous. I am measuring the length of the rod simultaneously at the two ends. In another frame it is not happening. It is bound to happen that you cannot measure the two readings simultaneously, and that's the relativity of simultaneity, which is giving rise to length contraction and time dilation. If you really understand relativity very clearly, because even after reading relativity for many years, people still can have many confusions. So what I suggest, it is better to resolve different paradox, then only you can get a deeper insight into relativity. So there are many paradoxes. I don't have any intention of discussing all those paradoxes, because if I keep on discussing those paradoxes, each one of them will take one class. So, and that's not our goal. So here I will just describe one of my favorite paradox, and I think if you can clearly explain this paradox, you can have a better insight into the special theory of relativity. So let me just describe this paradox and leave it to you for yes.
বলছি মানে যেটা এখানে সিডি ইভেন্টটা দেখা যাচ্ছে এটা কি প্রাইম ফ্রেমে কন্টিনিউয়াস ছবিটাতে মানে সাইমালটেনিয়াস হচ্ছে না তো, মানে যে ছবিটা সেখানে
কোনটা বলো, which one বলো, কোন এটা
হ্যাঁ সেটা, তো এটা তো সাইমালটেনিয়াস হচ্ছে না
কেন হচ্ছে না? এই CRD দুটো ইভেন্ট, this is cutting the time in this frame at this is time axis, x0 prime is the time axis in the prime frame, and CRD হ্যাঁ, যখন তুমি কোঅর্ডিনেটটা নেবে তখন তোমাকে অন্য অ্যাক্সিসটা প্যারালাল লাইন আঁকতে হবে। টাইম অ্যাক্সিস দেখতে গেলে কাট দেখতে গেলে তোমার স্পেসে প্যারালাল আঁকতে হবে, রাইট? তেমনি তুমি যদি স্পেস দেখতে গেলে টাইমে প্যারালাল আঁকতে হবে। ঠিক আছে, এটা একটু ভাবতে, আর কিছু না, তুমি একটু টাইম দিলেই বুঝতে পারবে। আমি যে বইটা বলেছি সেই বইটা ভালো করে খুঁটিয়ে দেখো, ওখানে সবগুলোটা খুব ভালোভাবে ডায়াগ্রাম দিয়ে বোঝানো আছে। কোনো ডাউট থাকলে আমরা পরে গেলে আলোচনা করতে পারি, রাইট? বাট স্টিল যখন আমি আলোচনা করছি, ইট ইজ বেস্ট টু আস্ক কোয়েশ্চেন, রাইট, সো দ্যাট আই ক্যান ক্লারিফাই ইউর ডাউটস। আচ্ছা, এই প্যারাডক্সটাতে আসি। মেনি অফ ইউ মে হ্যাভ হার্ড অ্যাবাউট ইট, বাট দিস ইজ ওয়ান অফ মাই ফেভারিট বিকজ অফ দ্য নাইস I mean, if you clearly understand this, so I'm first telling you the paradox. What is the paradox itself? So suppose you imagine two rockets, A and B, each of proper length. You remember, the proper length of A and B are 1 meter. Both have equal length in the rest frame. Okay. Now imagine both of them are moving in the opposite direction, and they have a relative velocity u. Okay. These are the input information that is given to you. Now, a missile is fired from the tail of rocket A as soon as the tail of rocket B crosses the tip of rocket A. তাহলে ব্যাপারটা বোঝো, বি রকেট, এই রকেটের লেন্থ সমান রেস্ট ফ্রেমে। বি রকেটটা যখন ক্রস করছে, ইট ইজ মুভিং ইন দ্য অপোজিট ডাইরেকশন। সো whenever the tail of B is crossing the tip of a missile will be fired from the tail of A. So the question is whether that missile will hit B or not. Now you look at the problem from the two different frames. If you look at the event from the frame of A, you see when the tail of rocket B reaches here at the tip of rocket A, both of them have equal length. So you may think that the both of them are lying side by side. Okay, both of them have equal length. But say from this frame, since this rocket is moving, so there will be length contraction. So this rocket will appear to be shorter from this frame. So if it fires a missile here from the end of the rocket, it should miss it, right? Because the length of B has contracted. So tip is reaching maybe somewhere here. So it will miss the rocket B. But again, if you see the same phenomena from the frame of reference of B, you see when the tail of B reaches the tip of A, it is the length of A which should get contracted, because B is looking at A and the length of A has contracted. If the length of A has contracted, the tail will come somewhere here, it is contracted, and then if it fires a missile, it should definitely hit B, right? A is telling no, it should not hit B, and B is telling it must hit itself. It must hit B. So how do you resolve this paradox? মানে এটা হতে পারে না যে একই সঙ্গে হিট করবে এবং মিস করবে, যে কোনো একটা জিনিস হবে। কোনটা হবে এটাকে ক্লিয়ারলি এক্সপ্লেন বাই taking into account the different events which are associated with here. I mean যখন ক্রস করছে টেলটা, তবে আমি তোকে হিন্টস দিয়ে রাখছি এখানে যে দুটো টিপ দুটো টেল, এই দুটো এইগুলো কখন ক্রস করছে তার উপর বেস করে ফায়ার করা হচ্ছে, কারণ এই টেলটা এখানে যখন পৌঁছাবে টিপের কাছে তখন রকেটটা ফায়ার করা হবে, মিসাইলটা ফায়ার করা হবে। সো নাও ইউ হ্যাভ টু রিজলভ দিস প্যারাডক্স by using your knowledge of relativity. See, paradox is there because you do not understand it clearly. If you understand it, there is no paradox, right? So this paradox, all the paradox in relativity are basically because of lack of understanding, because you do not see things in a proper way, because although we are studying relativity, but our common sense experiences tells us something else. So in the same way, this paradox can be resolved, and I am leaving it to you. I can give an explanation, but that will not help you to understand all these things which I have discussed in the last 2-3 classes, because I want you to understand. Probably many of you understand what I'm trying to say. Unless you think at different problems yourself, it is not possible to get a clear understanding of the subject. So that's why I'm just giving one example. You can have many paradoxes there. I mean, there are lots of paradoxes in relativity, and I am definitely not going to discuss all of them here. So this is just one particular paradox. Fine, I'm leaving it here. If you are not able to solve it, then I may discuss it in some other class, but not in this class. Let us move into the other topics that we need to discuss now. So I'm leaving this slide and starting some new one. Okay, let me close it, stop presenting. Okay. One minute. Why is not okay? Can you see the new slide?
Yes, sir.
Yes, sir.
আচ্ছা ঠিক আছে। আচ্ছা, if you have any question on the things that I have discussed till now, please ask. If you have any question, যদি কোনো প্রশ্ন থাকে, don't hesitate, just ask whatever comes to your mind. হ্যাঁ বলো।
স্যার যখন ওই হাইপারবোলা দিয়ে যে জিওমেট্রিটা পড়লেন ওই দুটো ফ্রেমে কেমন হবে, তো যখন ভেলোসিটিটা লাইটের ভেলোসিটির সাথে রিচ করবে, মানে এস প্রাইমের ভেলোসিটিটা যদি আমি ভি টেন্ডস টু সি নিই, তাহলে তো ওই মানে স্পেস আর টাইম মানে অ্যাক্সিস দুটো মার্জ করে যাবে, তো ওই জিনিসটা ঠিক বুঝতে পারলাম না।
আচ্ছা বলি, তোমার প্রশ্নটা হচ্ছে গিয়ে, আমি যদি দেখো রিলেটিভিটির বেসিক প্রিমাইসটা হচ্ছে তোমার একটা দেখে আপার লিমিট, রাইট? সো দ্যাট ইজ দ্য স্পিড অফ লাইট, রাইট? এন্ড নোবডি ক্যান রিচ দ্য স্পিড অফ লাইট, নাথিং, নো পার্টিকল, ইটস নট পসিবল, ইটস ইম্পসিবল in relativity, right? Now the question is that tends to c and equal to c are not same thing, right? Of course you can approach 0.99c, 0.999c, that's fine. And as when you are trying to achieve the speed of light, what will happen to the space-time axis in that frame? That is your question. Now, as I have shown you that as you increase the speed, alpha will increase, the angle of rotation will increase, right? So as the angle will increase, gradually they will approach the light, this wall line of light, that is a 45-degree angle line which you have drawn in the Minkowski diagram. And it will never exactly merge to the world line of light. It will go asymptotically go closer and closer and closer, but it will never merge to the world line of light. So definitely the space and time axis will be very close. I mean, they will be almost coincident, but definitely not exactly same. Right, this is the theoretical explanation. If you increase the speed and it tends to the speed of light, they will be nearly coincident to the world line of light, but never be exactly the same. Is the point clear?
ইয়েস স্যার। স্যার তাহলে ফোটনের জন্য তো এটা হবে না? ফোটন
তো ওই ওয়ার্ল্ড লাইনটা তো ফোটনের লাইন, ওটা তো কোনো মেটেরিয়াল পার্টিকুলার লাইন নয়। photon has a very special status in physics, right? Don't mix up photon with other things. I will come to this. Photon is something which is very special. The entire framework of relativity is standing on that, right? So don't mix up photon with any other particles, right? Any other material particle has to have velocity which is less than the speed of light or photon, right? So ফোটনের জন্য ওটা ফোটনের ফোটনের তো কোনো রেস্ট ফ্রেম নেই, আছে কি? ফোটনের কি কোনো রেস্ট ফ্রেম আছে? আমি যদি দুটো ইনার্সিয়াল ফ্রেম নিই, দুটো যদি ইনার্সিয়াল ফ্রেম নিই, তাহলে তুমি যে কোনো একটা ফ্রেমের রেস্টে নিয়ে যেতে পারো, তাই না? আমি এটাকে এস বলছি, এটা এস প্রাইম বলছি, আমি তো এস প্রাইমে গিয়ে বলতে পারি আমি রেস্টে আছি, বলতে পারি কি পারি না? পারি তো। কিন্তু তুমি ফোটনের ফ্রেমে গিয়ে বলতে পারি আমি রেস্টে আছি? দেয়ার ইজ নো রেস্ট ফ্রেম। ফোটনের জন্য কোনো রেস্ট ফ্রেম নেই, লাইটের কোনো রেস্ট ফ্রেম নেই, রাইট? তো তাহলে লাইট হ্যাজ এ ভেরি স্পেশাল স্ট্যাটাস। সুতরাং তুমি যদি ধরে নাও যে লাইট যাচ্ছে, মানে লাইটের ক্ষেত্রে তো স্পেস টাইম, লাইট ইজ ডিফাইনিং স্পেস টাইম, রাইট? স্পিড অফ লাইট ইজ ডিফাইনিং ইউর definition of space time, so you cannot treat it as a separate entity. Okay, fine. So now let us discuss about, হ্যাঁ বলো, হ্যাঁ বলো।
আমার কোশ্চেন হলো স্পেস লাইক ইভেন্টকে নিয়ে। হ্যাঁ,
হ্যাঁ।
সাপোজ আমার পৃথিবীতে দাঁড়িয়ে আমার বয়স 20 বছর। হ্যাঁ, কোনো মানে ডিস্ট্যান্ট কোনো একটা গ্রহে সেখানে কেউ একজন আছে, তার বয়স 40 ইয়ার্স। এইবার সেই ডিস্ট্যান্ট গ্রহে যে আছে, তো তার আর আমার যদি ডিস্টেন্স, হ্যাঁ স্পেশিয়াল ডিস্টেন্স যদি 20 লাইট ইয়ার্স এর থেকে বেশি হয়, হ্যাঁ, তাহলে সে আর আমি কে বড় কে ছোট, মানে বয়সে বড় কে ছোট, তো বলা কখনোই সম্ভব নয়।
আচ্ছা আচ্ছা, ঠিক আছে। তুমি তোমার প্রশ্ন ভালো প্রশ্ন, আমি ফিরে যাই, আমি আগে স্লাইডে ফিরে যাই, এটা আমার আলোচনা করা উচিত, এটা আমি বন্ধ করছি এখন। না ঠিক আছে, আমি তোমার প্রশ্নটা আনসার করছি, ওয়েট করো, আমি পুরোনো স্লাইডে ফিরে যাই, যখন প্রশ্নটা এসছে আই শুড অ্যাড্রেস ইট। ওকে, আমি পুরোনো স্লাইডে যাচ্ছি, তোমার দেখতে না পেলে বলবে। দেখা যাচ্ছে স্লাইড, দেখা যাচ্ছে তো? আচ্ছা, হ্যালো, দেখা না গেলে বলো। আচ্ছা দেখা যাচ্ছে, ফাইন। আচ্ছা, অভিষেক যে প্রশ্নটা করছে সেটা আনসারটা আমি বলি। আচ্ছা, ফার্স্ট অফ অল, ওকে, লেট মি জাস্ট ফার্স্ট গো টু দিস পিকচার। তাহলে আমরা স্পেস, হাউ উই ডিফাইন দ্য স্পেস লাইক ইভেন্ট, রাইট? সো স্পেস লাইক ইভেন্টস আর দ্য ইভেন্টস ফর হুইচ, দেখা যাচ্ছে না?
না স্যার, আসেনি।
ও দাঁড়াও, তাহলে আমি ভুল করছি, দাঁড়াও, তাহলে আমাকে প্রেজেন্ট করতে হবে এটাকে। উইন্ডো, দাঁড়াও, ভিউ, এখন দেখা যাচ্ছে? আচ্ছা, ঠিক আছে, ওকে, ঠিক আছে। আচ্ছা আচ্ছা, আমি বাংলা ইংরেজি মিশিয়ে বলছি, ঠিক আছে? হোয়াট ইজ হাউ ডু ইউ ডিফাইন স্পেস টাইম ইন্টারভাল, রাইট? সো স্পেস লাইক সেপারেশন, অ্যাজ obviously সাজেস্টিং দ্যাট দেয়ার আর টু ইভেন্টস হুইচ আর স্পেস লাইক সেপারেটেড, 20 লাইট ইয়ার্স থেকে বেশি সেপারেটেড, এর বয়স 20 বছর, বয়স 40 বছর। আচ্ছা, ভালো কথা। তাহলে স্পেস লাইক সেপারেশন, এটার মানেটাই হচ্ছে যে, তার মানে এই আমি ছবিটা গেছিলাম, এখানে স্পেস লাইক কোথায় গেল? এই যে স্পেস লাইক, this one. So delta x is larger than c delta t. ওই দুটো ইভেন্টের মাঝখানে যে টাইম সেপারেশন, সেটা সঙ্গে c দিয়ে গুণ করলে সেটা ছোট হবে as compared to the spatial separation between the two events. Okay, now ওকে, আমরা যেটা শিখলাম যে হাইপারবোলিক নেচার অফ স্পেস টাইম এন্ড রোটেট করে যায়, এটা আমরা ভাবা যাক একটু, ঠিক আছে? তাহলে ধরে নাও সিটি এন্ড এক্স আর দ্য স্পেস এন্ড টাইম অ্যাক্সিস ইন দ্য আর্থ ফ্রেম, যেখানে কিনা এই যে 20 বছর বয়সের ছেলেটি বসে আছে, ঠিক আছে? দিস ইজ দ্য রেস্ট ফ্রেম। ওকে, ফাইন। And the another guy who is sitting in some other galaxy or
স্যার শোনা যাচ্ছে না।
other planet who 20 light years থেকে বেশি ডিসটেন্সে বসে আছে, তাহলে ধরা যাক এই
হ্যালো স্যার, হ্যালো স্যার।
বাকিরা শুনতে পাচ্ছিস? হ্যালো?
হ্যাঁ রে,
হ্যাঁ সবাই শোনা যাচ্ছে। স্যার তো বেরিয়ে গেল মনে হচ্ছে।
হ্যাঁ, মনে হচ্ছে
হ্যাঁ স্যারের নেটওয়ার্ক মনে হচ্ছে প্রবলেম হয়ে গেছে।
কারেন্ট ফারেন্ট চলে গেলে বোধহয় ব্রডব্যান্ড ওয়াইফাই বন্ধ হয়ে গেছে।
ব্রডব্যান্ডে ব্যাটারি থাকে না?
না না,
স্যার কি কলেজ থেকে পড়াচ্ছে নাকি? এটা ইউনিভার্সিটি থেকে ক্লাস করাচ্ছে না বাড়ি থেকে?
না না, বাড়িতেই বোধহয় দিন।
জিওর নেটটা তো ভালো, জিও ফাইবারটা। ব্রডব্যান্ড তো মাঝে মাঝে ডিস্টার্ব দিচ্ছে খুব।
স্যার আছেন, চুপ কর কিংসু।
আচ্ছা, তোমরা এখন কি আমাকে শুনতে পাচ্ছ? হ্যালো?
হ্যাঁ স্যার, এখন
হ্যাঁ হ্যাঁ হ্যাঁ, এটা 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 নেটওয়ার্কের সমস্যা নয়, আমার আসলে ফোনের থেকে আমি ইউজ করছিলাম, হেড অফ দ্য ডিপার্টমেন্ট ফোন করেছিলেন, ফোন রিসিভ করতে যাওয়ার জন্য নেটওয়ার্কটা স্লো হয়ে গেছিল, ওই জন্য কেটে যাচ্ছিল। ঠিক আছে, আমরা কন্টিনিউ করি। প্রেজেন্ট নাও। কোথায় গেল? জাস্ট এ মিনিট, ওকে আবার নতুন করে এটা খুলতে হবে, খুলছে না কেন এটা? প্রেজেন্ট নাও কোথায় গেল? আসছে না কেন? এক মিনিট। something is happening. আমাকে এটা পারমিশনটাকে পারমিশনস অটো ব্লক কোথায় গেল? ওকে, এখন দেখা যাচ্ছে?
হ্যাঁ স্যার, হ্যাঁ স্যার।
আচ্ছা, ঠিক আছে, আমাদের আলোচনায় ফিরে আসা যাক। সো as you transform to a new inertial frame which is moving with respect to the rest frame, your space and time axis gets orthogonal to the coordinate system in the rest frame. So you see, if I take an event here, suppose for example this event, this is a time like event, right? So I can always boost to a frame. So আমি আগে বলেছি তোমাদেরকে যে টাইম অ্যাক্সিসটা আর স্পেস অ্যাক্সিসটা অর্থোগোনাল হয়ে যায়, নন অর্থোগোনাল হয়ে যায়। তাহলে ধরুন এমন একটা ফ্রেমে গেলাম যেখানে টাইম অ্যাক্সিসটা এই পয়েন্টের মধ্যে দিয়ে যাচ্ছে, এটার মানেটা কি? যদি একটা এমন ফ্রেমে যায় যেখানে টাইম অ্যাক্সিসটা এই পয়েন্টের মধ্যে দিয়ে যায়, তার মানে কি এই পয়েন্টটা যেটা আমার প্রেজেন্ট আর এই পয়েন্টটা দুটো কিন্তু টাইম অ্যাক্সিসের উপর লাই করছে, তাই তো? তার মানে কি, এটা মানেটা কি? আর আমি যদি আরেকখানা তার মানে আরেকখানা ফ্রেম ভাবি, ধরুন একটা স্পেস লাইক ইভেন্ট, আমি যদি ওই একটা নতুন ফ্রেমে যাই যেখানে কিনা আমার স্পেস অ্যাক্সিসটা এই পয়েন্টের মধ্যে যায়, তার মানে এটা কি? আমার স্পেস অ্যাক্সিসটা এর মধ্যে দিয়ে যাওয়া মানে কি হচ্ছে? তার মানে দে আর সাইমালটেনিয়াস হ্যাপেনিং এট দ্য সেম টাইম, অনলি গ্যাপ বিটুইন দ্য টু ইভেন্টস আর দ্য স্পেস লাইক, they are separated by some amount of space delta x. Similarly, in this case, when your time axis goes through the point, this point, even say p here, then it's a time like, why that time like? The only difference is in time, there is no spatial separation because they are happening at the same location. You see, both are lying on the same line, so they are happening at the same location in the prime frame. The only difference is the difference in time. That's why they are called time like. Now coming back to Abhishek's question, so what he's trying to say that whether the two events can be the order can be reversed or not. Yeah, that I already told you that the space like separated events, if you choose another frame, it is always possible to allow a reversal of the two events, and that doesn't harm anything because that preserves causality, because these two events are not causally connected. So okay, let me explain it geometrically. So suppose you boost to a frame, so in this frame, so this event is, there is a clear time order, right? This is happening first and then this is happening, right? With time order along the time axis, they are at different location, so they are happening, this one is first and this one is next. But I can jump to a frame where my space axis say goes above this point, ধরো এইভাবে যাচ্ছে, পয়েন্টের উপর দিয়ে যাচ্ছে। এই পয়েন্টের উপর দিয়ে যদি যায় তাহলে আমি যে টাইম কোডেড গুলো পাবো বাই ড্রয়িং প্যারালাল লাইনস টু দ্য স্পেস অ্যাক্সিস, এখানে একটা লাইন ইমাজিন করো যেটা কিনা এই পয়েন্টটাকে ক্রস করে গেছে, তাহলে সেটা তোমার নতুন স্পেস অ্যাক্সিস ইন দ্য প্রাইম ফ্রেম। এবার যদি এই পয়েন্ট থেকে তুমি যদি ওই নতুন নন অর্থোগোনাল ফ্রেমে তুমি যদি ড্র করো, কারণ তখন তোমার এইটা যদি এটা স্পেস অ্যাক্সিস হয় তাহলে টাইম অ্যাক্সিসটা এরকম হবে, এর কাছাকাছি। ধরো এটা 60 ডিগ্রি, তাহলে সরি 60 ডিগ্রি কখনো হতে পারে না, ওকে 30 ডিগ্রি, তাহলে এদিকেও 30 ডিগ্রি হবে। তাহলে এই লাইনটাকে, এটা তোমার টাইম অ্যাক্সিস, এটা যদি পিছন দিয়ে বাড়ানো যায় তাহলে এটা নেগেটিভ পাস্ট অ্যাবসলিউট পাস্ট। তাহলে সেখানে যদি আমি এবার এটাকে এর স্পেস অ্যাক্সিসের প্যারালাল লাইন ড্র করি তাহলে এটা কাট করবে সেই টাইম অ্যাক্সিসে, সেইটা কিন্তু অন্য জায়গায় কাট করবে। দেখো এখানে এটা আগে এটা পরে হচ্ছে, ওখানে যদি তুমি দেখো তাহলে এটা আগে হবে ওটা পরে হবে। So you can always find a valid inertial frame where the two space like separated events are reversed and there is no harm in it. অভিষেক যেটা বললো যে এখানে 20 বছর ওখানে 40 বছর, যে মাঝখানে 20 লাইট ইয়ার্স থেকে বড় গ্যাপ যদি থাকে, তাহলে দিস ইভেন্ট ইজ নট গোয়িং টু ইনফ্লুয়েন্স দ্যাট ইভেন্ট ইন এনি ওয়ে, because light cannot travel from this event to that event, right? So you cannot surpass the speed of light. There is no other mechanism by which you can influence the second event by the first event. So if that is the case, there is no harm in changing the order of the two events. You are not changing it. Relativity is allowing it. You can go to another frame from which the second event may happen first and the first event may happen later. There is no problem at all with that. Right? So it is all about this orthogonal to non-orthogonal transformation. Right? So space-time axis gets squeezed towards the world line of light, and as you do that by larger and larger velocity, what will happen is that the ordering between two space-like events can be changed. Is the point clear? If not, please ask what are the doubts.
তার মানে স্যার আমরা মানে কে বড় কে ছোট এটা বলতে পারি না এক্স্যাক্টলি যে কে বড় হবে কে ছোট হবে।
কে বড় কে ছোট, দেখো টাইম, হাউ ডু ইউ ডিফাইন টাইম? দিস ইজ ইউর প্রেজেন্ট, রাইট? ইন ইউর ফ্রেম, দিস ইজ ইউর অ্যাবসলিউট ফিউচার, দিস ইজ ইউর অ্যাবসলিউট past, right? All the events which could have influenced your present, all the events which could be influenced by this event, your present. But there are many other events in the universe which are not causally connected to you. So if an event is not causally connected to you, it doesn't matter. From another inertial frame, you can always find out another frame where the two events may not happen in the same order. So how do you compare when they are not causally connected? K boro K choto, how can you compare? Because the two frames are different, right? And they are causally disconnected event. So the comparison itself is meaningless. Right? You have to think it clearly. Right? You have to think it clearly, right? Those kind of comparison have no place in relativity, right? It is allowed, right? That is what all relativity is saying. Is that point clear?
হ্যাঁ ঠিক আছে।
ওকে, ঠিক আছে, আমি নেক্সট স্লাইডে যাই, এটাতে বন্ধ করে দেওয়া যাক। হ্যাঁ বলো বলো।
বলছি যখন আমরা রিলেটিভিটি, স্পেশাল থিওরি অফ রিলেটিভিটি তো আমার ইনার্সিয়াল ফ্রেমে, কিন্তু যখন ইনভার্সিটি ডায়াগ্রাম করছি, রোটেশন ঘটছে, তখন তো ওখানে একটা নন ইনার্সিয়াল চলে আসছে।
কোথায় নন ইনার্সিয়াল চলে আসছে বাবা? কোথায় বাবা নন ইনার্সিয়াল
হচ্ছে আমার?
রোটেট হলো, রোটেশনের সঙ্গে নন ইনার্সিয়াল কি সম্পর্ক?
মানে সেখানে তো একটা অ্যাঙ্গুলার অ্যাক্সেলারেশন, সেন্টিপিটাল অ্যাক্সেলারেশন বা সেন্টিফিউজাল অ্যাক্সেলারেশন তো আছে।
না, তুমি সব ভুলে ফেলেছো। স্পেস টাইম তো আর কোনো একটা মানে মেটেরিয়াল পার্টিকেল নাই, রোটেট করছে ঘুরছে তাই অ্যাঙ্গুলার অ্যাক্সেলারেশন চলে এলো, তা নয়। স্পেস টাইম itself is something where, I mean, you see, space and time provides you the stage where everything takes place, right? Energy, matter, যা কিছু ড্রামা তুমি দেখছো, right? Space time is a dynamic stage, it's not a fixed stage, right? So that is what all relativity is saying to you. স্পেস আর টাইম রোটেট করছে মানে ঘুরছে না, যে তার অ্যাক্সেলারেশনের কোনো প্রশ্নই নেই। এখানে বলা হচ্ছে ইনার্সিয়াল ফ্রেম কে অ্যাক্সেলারেশন দিয়ে ডিফাইন করা হয় না। ইউ মাস্ট হ্যাভ টু হ্যাভ ইউনিফর্ম ভেলোসিটি, অর দ্য টু ফ্রেমস হুইচ আর এট রেস্ট ক্যান বি কল্ড ইনার্সিয়াল ফ্রেম। এখন এই ডায়াগ্রামটার মাধ্যমে দেখানো হচ্ছে যে যদি তুমি একটা ইনার্সিয়াল ফ্রেম থেকে আরেকটা ইনার্সিয়াল ফ্রেমে যাও, তাহলে স্পেস অ্যাক্সিস আর টাইম অ্যাক্সিসের যে তোমার যে স্ট্রাকচারটা ছিল, যে তুমি যে দুটো অর্থগোনাল ছিল, সেটা অর্থগোনাল না হয়ে নন অর্থগোনাল হয়েছে। তার মানে না এই নয় স্পেস আর টাইম অ্যাক্সিস ঘোরা শুরু করলো, তা কিছু হচ্ছে না, জাস্ট একটা অ্যাঙ্গেলে রোটেট করে যাচ্ছে। তোমার মেজারমেন্ট, যেটা আমি আগে বলেছিলাম, ফর এক্সাম্পল এইখানে বলেছিলাম, এখানে এটা কি রোটেশন মানে কি নন ইনার্সিয়াল হতে হবে? তা তো নয়। কোথায় গেল এক্সাম্পলটা? এখানে নেই, পরেরটাতে আছে। যাও, না এখানেই ছিল কি? হ্যাঁ এখানে ছিল। এই যে আমরা রোটেশন দিচ্ছি, স্পেস অ্যাক্সিসটা ঘুরে গেল, টাইম অ্যাক্সিসটা ঘুরে গেল। এটা ইউক্লিডিয়ান স্পেস হওয়ার জন্য দুটো একই দিকে ঘুরছে। লরেন্স যে তোমাকে ট্রান্সফরমেশন যেটা বলে, সেটা হচ্ছে কি স্পেস টাইম মানে সেটা হাইপারবোলিক, যে কারণে এটা দুটো একই দিকে ঘুরবে না। এটা এদিকে ঘুরলে ওটা উল্টো দিকে ঘুরবে, রাইট? এটাই শুধু বলা হচ্ছে। এখানে কেউ ঘোরাঘুরি করছে না, যার অ্যাক্সেলারেশন চলে আসবে। স্পেস আর টাইমের অ্যাক্সিস দুটো রোটেট করে যাচ্ছে উইথ রেসপেক্ট টু দ্য রেস্ট ফ্রেম। রেস্ট ফ্রেমে আমার যে স্পেস টাইমের যেটা ছিল তোমার, সেটা থেকে শিফট করে যাচ্ছে, চেঞ্জ হয়ে যাচ্ছে, এবং সেটা চেঞ্জ হওয়ার জন্য তোমার ইউনিট অফ টাইম এন্ড ইউনিট অফ স্পেস সেটাও চেঞ্জ করে যাচ্ছে, যার কারণে মেজারমেন্ট গুলো আলাদা আলাদা হচ্ছে। যেমন এখানে তুমি ক্লিয়ারলি দেখতে পাচ্ছ, কি দেখতে পাচ্ছ? আমি যখন নতুন ফ্রেমে গেলাম, পি এর কোঅর্ডিনেট কি সেম? তুমি দেখো একটা বেড়ে গেছে, একটা কমে গেছে, দেখতে পাচ্ছ। এখানে আগে ছিল ও এ, তুমি বলছো এখন ও সি, তাই তো? তুমি দেখো এখানে আগে কি ছিল? এটা ছিল পি এ, এটা হয়ে গেছে এখন পিসি। তার মানে কোঅর্ডিনেট গুলো পাল্টে পাল্টে যেতে পারে। তো স্পেস আর টাইমে তো কোঅর্ডিনেট, সেটাই বলা হচ্ছে যে স্পেস একটা কোঅর্ডিনেট, তুমি আগে টাইমটাকে আলাদা ভাবছিলে, স্পেসটাকে আলাদা ভাবছিলে। স্পেস আর টাইম দুটোই কোঅর্ডিনেট। তুমি যখন একটা ফ্রেম থেকে মাপছো তখন তার কম্পোনেন্ট, যেমন তার মানে স্পেস টাইম আমরা 4 ভেক্টর বলবো এবার থেকে। এখানে যেমন ধরো 2 ডাইমেনশনে কাজ করছে, দুটো তার এটা 2 ডাইমেনশনাল ভেক্টর, তার দুটো কম্পোনেন্ট, তার দুটো নাম্বার দিয়ে তুমি রিপ্রেজেন্ট করছো। এখানে আমি 4টা নাম্বার দিয়ে রিপ্রেজেন্ট করবো। সুতরাং কম্পোনেন্ট গুলো ফ্রেম থেকে ফ্রেমে পাল্টে যেতে পারে, কিন্তু ভেক্টরের লেন্থটা একসাথে পাল্টাবে না। এবং রিলেটিভিটিতে ভেক্টরের লেন্থটা x² + y² নয়, x² - y²। দ্যাট ইজ দ্য ডিফারেন্স, রাইট? সেটা হাইপারবোলিক নেচারের হওয়ার জন্যই তুমি মাইনাস সাইনটা পাচ্ছ, যেটা কিনা ইউক্লিডিয়ান জিওমেট্রি থেকে ডিস্টিংক্টলি আলাদা। আর এখানে যেটা আমরা বলছিলাম, কোথায় গেলাম, এখানে না, হ্যাঁ, তার মানে এখানে কোনো রকমের কোনো নন ইনার্সিয়াল ফ্রেম নিয়ে আলোচনা হচ্ছে না। রিলেটিভিটি নন ইনার্সিয়াল ফ্রেম নিয়ে কথা বলে না, তার জন্য তোমাকে জেনারেল রিলেটিভিটি যেতে হবে, কারণ সেখানে তোমার ল অফ ইনার্সিয়া হোল্ড নাও করতে পারে, ফিক্সিয়াস ফোর্স অ্যারাইজ করতে পারে, সেগুলো আমরা আলোচনা করছি না এখানে। তোমার যেটা ডাউট ছিল সেটা ক্লিয়ার?
ওকে স্যার।
না, যদি কোনো প্রশ্ন থাকে ইউ ক্যান স্টিল আস্ক, রাইট? দেয়ার ইজ নো হার্ম ইন আস্কিং কোয়েশ্চেন, রাইট? তুমি যদি স্যাটিসফাইড হও অ্যানসার নিয়ে ফাইন, তোমার যদি ডাউট থাকে ইউ ক্যান স্টিল আস্ক।
না, আমি স্যার বলতে চাইছিলাম যখন রোটেশনটা হতে শুরু করছে এক জায়গায় মাঝখানে ধরলাম কনস্ট্যান্ট থাকছে থিটাটা, কিন্তু
আচ্ছা।
মানে যখন শুরু হচ্ছে বা যখন স্টপ হচ্ছে রোটেশনটা,
না, না,
তখন তো সেই চেঞ্জ অফ
না, তাহলে তুমি তার ঠিক জিনিসটা বোঝোনি। তোমাকে আমি বলছি, আবার ঘুরে বলছি, আমার কথাটা ক্লিয়ারলি শোনো আগে। কোনো ঘুরতে শুরু করছে না কিছু, যে মুভ করা শুরু করলে মানে স্পেস টাইম ঘোরা শুরু করলে ঘড়ি কাঁটার মতো তা নয়। এখানে যেটা বলা হচ্ছে যে যখনই তুমি একটা ফ্রেম থেকে একটা ফ্রেমে যাবে, বেস্ট অন দ্য ভেলোসিটি, তুমি খেয়াল করে দেখো এখানে একটা অ্যাঙ্গেল লিখেছি আমি, কোথায় গেল, হোয়াট ইজ দ্য অ্যাঙ্গেল, এখানে তুমি দেখো কি বলা হয়েছে, অ্যাঙ্গেলটা দেখো এখানে, আলফা = tan ইনভার্স বিটা। তাহলে যখন তোমার ধরো তুমি v = 0.5 c নিয়ে এক্স ডাইরেকশনে যাচ্ছ, তার মানে তোমার আলফাটা ফিক্সড হয়ে গেল। এটা ঘুরতে শুরু করবে কেন? আলফাটা ফিক্সড। যখন তুমি একটা অন্য ফ্রেমে গেলে, দ্য মোমেন্ট ইউ সুইচ টু অ্যানাদার ফ্রেম হুইচ ইজ মুভিং উইথ ইউনিফর্ম ভেলোসিটি, তাহলে 0.5 c এই ইউনিফর্ম ভেলোসিটি নিয়ে মুভ করছে প্রাইম ফ্রেমটা। তাহলে তার জন্য আলফা যা ভ্যালু হওয়া উচিত তাই হবে। সি অ্যাঙ্গেলেই এটা তুমি দেখবে এটাকে, স্পেস আর টাইমটাকে। ওই ফ্রেমে গেলে রোটেট করে যাচ্ছে, মানে আমি বলছি ঘড়ি কাটার মতো কিছু ঘুরছে না। তুমি যখন রেস্ট ফ্রেমে আছো তার যে স্পেস টাইম অ্যাক্সিস, আর যে মুভিং ফ্রেমে আছে ইনার্সিয়াল ফ্রেমটাতে তার যে স্পেস টাইম অ্যাক্সিস, তাদের মধ্যে একটা অ্যাঙ্গেল আছে, এটাই বলা হচ্ছে। রোটেট করে যাওয়া মানে এটা বোঝা যাচ্ছে না যে এই ফ্রেমটা, বুঝা গেছে? ক্লিয়ার? ওকে, ঠিক আছে, ওকে। তাহলে এখান থেকে আমি বেরিয়ে যাই, এটাকে স্টপ করি, অন্যটাকে ওপেন করি, দাঁড়াও। প্রেজেন্ট, দেখা যাচ্ছে নতুন? আচ্ছা, ঠিক আছে, ওকে। সো নাও লেট আস বিগিন our journey in 4 dimension. So from now onwards we will be looking at different quantities in 4 dimension, for example velocity, acceleration, force, momentum, and whatever we have learned in Newtonian relativity must have a 4-dimensional counterpart. And it is very important to understand their form and their interrelationship between different these quantities to understand the different physical phenomena or kinematic events that can happen. So এখানে x mu আমি একটা মিউ দিয়ে লেবেল করছিলাম। আই থিংক তোমরা হয়তো টেনসর পড়েছো আগে, টেনসর না ভেক্টর, এখানে 4 ডাইমেনশনাল ভেক্টর বলছি, এখানে টেনসর বলতে টেনসর অফ ফার্স্ট র্যাঙ্ক, সেকেন্ড র্যাঙ্ক, সে তো ভেক্টর টেনসর হতে পারে। তো এখানে যেটা বলে রাখা উচিত যে x mu is a vector, 4 vector, আমাদের স্পেস টাইম ভেক্টর is a 4 vector which has 4 components. So what is the criteria to be a 4 vector? If I give you 4 different numbers, say 5, 6, -7 and 9, so can it represent a 4 vector? The answer is no. You cannot define an arbitrary vector with 4 numbers to be a 4 vector. In order to be a valid 4 vector, the most important criteria is that when you transform between different inertial frame, the components of the vector must transform according to the Lorentz transformation. That's the most important criteria to be a valid 4 vector. And space-time 4 vector is already a valid 4 vector because that obeys Lorentz transformation, right? And these are the 4 components. So x mu, generally the contravariant and covariant components of a vector are denoted by superscript and subscript. So x mu denotes the contravariant component. I hope you understand what meant by contravariant and covariant components from previous discussion in mathematical physics or other courses. So x mu are the contravariant components of the 4 vectors, space-time 4 vectors. And x lower mu are the covariant components, ct minus x minus y minus z. And when I take a scalar product or dot product between the two contravariant components and covariant components, that is the way the product of vectors defined. So x mu in relativity, so you get c square t square minus x square minus y square minus z square, which is nothing but c square t square minus r square. And we have already seen that this quantity is a Lorentz invariant quantity. This doesn't change from one inertial frame to other, right? So c square t square minus r square is already known as space-time interval. And this is nothing but the norm of the 4 vector, or the length of this gives you the length of the 4 vector. Just like length of a line doesn't change. If I say I draw a line on the piece of paper and I rotate the page or translate the page from one table to other, the length of the straight line is not going to change, right? Only its component change. See, in the similar fashion here also the length of a 4 vector doesn't change, and that's a very empowering thing. The length of a 4 vector doesn't change. Only its components can change, and they can change in a certain way, which we already know. There will be Lorentz transformation, so you can relate the components between different inertial frame. So the same principle applies to any 4 vectors. And just like the way we defined space-like event, separated event, time-like separated event, and like separated event, you can also define a space-like 4 vector, time-like 4 vector, or light-like 4 vector. Criteria are very similar, and that means the length of the 4 vector, if it is positive, negative, and 0, then based on the values of the length or norm, you can call a 4 vector to be space-like, time-like, or light-like. It's just a nomenclature, so there is not much physics behind it. So it's just nomenclature. Okay, so I mean, just like space-time 4 vector, we can define many other 4 vectors. So for the time being, let us discuss about 4 velocity, right? So in order to understand 4 velocity clearly, you should first understand what we mean by 3 velocity. All of us understand 3 velocity, right? How do I define 3 velocity? We divide the space interval by time interval in a frame and then calculate what is the velocity, right? So of course there you can take instantaneous values, small infinitesimal increase in position and time, and then take a ratio to get the velocity. But how do I calculate velocity in 4 dimensions? Especially when length and time are not some different frames, right? Suppose there is a particle which is moving and moving from say point A to B, and there are 2 frames, right? One frame is say at rest, another frame is moving with velocity 0.9 c along say x direction. And the 2 persons, if they measure the distance between A and B, obviously their conclusion, their measurement will be different, right? Also there is time dimension, so time is not same, length is not same. So how do we measure the velocity of a particle? That's the question in relativity. Now to address this issue, so what is done is we define something called 4 velocity, and it's a 4 vector. How do we ensure that's a 4 vector? That is the way it is defined. How it is defined? Okay, so let me just tell you the definition first. So u mu is the contravariant components of the 4 velocity, is defined as dx mu d tau. What is dx mu? Dx mu is an infinitesimal small space time interval. Remember, it's not space interval, space time interval, like infinitesimal space time interval between 2 events in one frame. Say it's lab frame, you can choose any other frame. So in the lab frame, dx mu represents the infinitesimal space time interval. Okay, and what is d tau? D tau is the infinitesimal time increment in a specific frame in which both events take place at the same location. What do I mean by that? Okay, let me just give one example. Suppose you are riding a train which is which can move very fast. Okay, maybe I can take a slower moving train as well, because that doesn't change the underlying meaning. So suppose you are a person who is traveling by a train, so you start at say Santiniketan and going to Calcutta along a straight line, right, with some velocity, say 0.5 c, meaningless anyway, but anyway it's moving. So the person who is sitting inside the train, and suppose you start reading a story book at Santiniketan, and you finish that book when you reach Howrah. Okay, so from Santiniketan to Howrah, that's a distance, and suppose it's 200 kilometers, which is measured by some observer outside the train. So I'm standing inside on the platform and measure the distance between Santiniketan and Howrah by sending a light signal and calculate it to 200 kilometers. Fine. But the person who is inside the train, okay, so let us consider two events: when you start reading the book and when you finish reading the book. So when you start at Santiniketan and then reach Howrah, those are the events from the person who is standing on the platform. But the person who is, suppose the train is closed, the person inside the train cannot see anything outside, so he doesn't know what is Santiniketan and what is Howrah. Everything is same, right? And when it is moving with uniform velocity, that person is the same like any other inertial frame, right? So suppose the person starts reading a book at Santiniketan and finish the book at Howrah from the outside observer. So these are the two events: starting reading and when he finishes the reading. So see, from the person who is inside the train, his perspective will be both the events are taking place at the same location, because he has not moved an inch. He is sitting on the same chair, right? Although train has moved for say 200 kilometers for the outside observer, that person inside the train is sitting at the same position. So for him, the two events take place at the same location. That's what I'm trying to say, that the events are happening at the same location. So the time which he measures is the proper time. The proper time is what? It's a time in the rest frame of the observer. So the person which is inside the train, if he measures the time difference between these two events, what he will measure is the proper time, right? Because the time is measured in his own rest frame. And there is no special separation between the two events. So that's what I'm trying to say. So b tau is the proper time, right? Proper time, to just make it clear. And dx mu is the infinitesimal space-time interval between two frames in the lab frame. In this example, lab frame is the person who is standing on the platform, who is measuring from outside. So in this case, you see, if I look at this definition, dx mu d tau, you see and if you know the quantity which is invariant, ds square equal to c square dt square minus dx square minus dy square minus dz square, and if the two events are taking in the same place, then we have no special separation, that's 0. So time is the proper time, c square d tau square, which is again invariant. So in one frame, c square d tau square, another frame c square dt square minus dr square. And we know already the relationship between the proper time and the time, but again I have shown it again. D tau equal to dt by gamma u. I use this u to denote because see, there could be two different velocity associated with the so one attached with the particle, another with the transformation. Suppose two different inertial frame is measuring the velocity of a single particle which is moving with velocity u. So in that case, there are two velocity associated in this picture. One is the velocity with which a frame is moving, another is the velocity of the particle which is moving in these two frames, right? So we have to connect the velocity and its different components, so we should be clear. When I write gamma u, it's the velocity u, right? So velocity of the particle in this case. So u0 is simply how do I calculate u0? Use a time component of the force velocity. So you know dx0 is c dt. So if you differentiate c dt, c is a constant, it will come outside. So d dt of basically ct, so d dt c of d dt d tau, and dt by d tau is nothing but gamma, because that's the relationship between proper time and time in other frame. So that becomes c into gamma u. u1 is the again d dt of the spatial coordinate dx dt. So here d tau. So since you are using d tau, it will throw out a factor gamma. I'm sorry, here I have forgotten to write u. So that it will be u. Gamma u, gamma u, gamma u. Think of the gamma u, right? So u1 will be gamma u x, u2 will be gamma u y, u3 will be gamma u uz. So these four numbers give you a 4 vector which we call 4 velocity. and it is a hybrid quantity. Remember, the two things are measured in two different frame, right? So space-time 4 vector which you have taken on the numerator is measured in the lab frame, and the proper time which you have taken is in the particles frame, where the particle itself is at rest, right? You are seeing the particle to be moving, but in particle's own frame, it is not moving. So it is measuring the time interval between the two events in its own frame. That's why it's proper time. And the numerator is the space time 4 vector that you are measuring from the lab frame. That's why you see x0 equal to ct, x1 equal to x, x2 equal to y, x3 equal to z. And tau, when you differentiate that space-time 4 vector with respect to proper time, you get a 4 vector whose components are gamma uc, gamma u ux, gamma u uy, gamma u uz. Right? So ux, uy, uz are the usual free velocity. If the person who is standing on the platform measures the velocity of the person who is moving, sitting inside the train, that is the free velocity, or the person or the particle, whatever you take. I'm just giving one example. You can take anything else, right? So ux, uy, uz are three velocities. Gamma is the Lorentz factor corresponding to velocity u, and gamma you see that's the time component of 4 velocity, right? Time component of 4 velocity. And I have just made the notation sorted by taking gamma u outside the expression here. So gamma u c, ux, uy, uz are the three the components of 3 velocities. So I can write just the u vector. So it is 3 components. So gamma u inside the bracket c comma u, that's the 4 velocity. And it is a hybrid quantity and has enormous advantage over ordinary velocity. Why? Simply because when we deal with motion of particles in 4 dimensions, we have to apply the concepts of relativity. And in relativity, we have Lorentz transformation. So the kind of physical quantities that we want to use in 4 dimensions, if they have a 4 vector character, then it will be easier to handle them, right? So if we have a 4-dimensional counterpart of velocity, which we call 4 velocity, then it will obey the Lorentz transformation. When we can transform from one inertial frame to other, the different components of 4 velocity will transform according to Lorentz transformation, and our life will become much simpler than usual case in 3 dimensions. I will show you how and why, right? Okay, so let me write down the transformation equation for 4 velocity. They are exactly similar. So consider the two frames S and S prime. So S is a frame at rest, S prime is a frame which is moving with velocity v along the x-axis. And consider a particle which is moving with velocity u along some arbitrary direction. Okay, so you want to measure the velocity of this particle from these two different inertial frame, and want to relate the measurement between the two frames. How do we do that? As I told you, once you construct a 4 velocity, not the 3 velocity, you can easily relate the components by simply using Lorentz transformation. So here I am writing u0, u1, u2, u3. These are the 4 space-time components of the 4 velocity. When I use a prime, I denote them for the prime coordinate. Without any prime, they are the quantities in the unprimed frame. You can see very similar equations just like space-time 4 vector. If you remember, look at this. I have already. That's in a different slide. Fine. So you see u0 prime is gamma. See, this is gamma v. So don't get confused between gamma u and gamma v. Gamma u is the Lorentz factor associated with the velocity of the particle, and gamma v is the Lorentz factor associated with the relative velocity of the inertial frame which is moving. That is, the S prime frame is moving with velocity v. So that's why I'm writing gamma v. So you should distinguish between gamma u and gamma v. Please correct this one. I forgot to put a u here. Gamma u, gamma u, gamma u. Okay. So this is Lorentz nothing but Lorentz transformation equation. Since the motion is happening along the x direction, only x component and the time component would change. Y component, z component remains unchanged. They are similar equations, so I am not repeating what is written here. You can easily understand the transformation between the different components. Okay, now let us rewrite the relationship between the different components in 3 dimensions by relating this. Okay, you can see this is a much simple looking equation, right? So from the first equation, you see u0 prime. What is u0? It's a time component of 4 velocity. And what is that? C gamma or gamma C. So if I am in prime frame, C is not going to change. There is no C prime. C is same. C gamma U prime. So I have written on the left hand side of the first equation C gamma U prime. And what are the quantity in the right hand side? Gamma V. What is U0? C gamma U. What is beta? Beta remains beta. What is U1? Gamma U into Ux. So I have taken gamma U outside. So C gamma U outside. So C gamma U gamma V, that will be 1 minus beta is V by C. So since I have taken a C outside, it will be V by C square. Beta is already V by C. V by C square into Ux. That means if I cancel C from both sides, gamma U prime will be gamma U gamma V into 1 minus Ux V by C square. In the same way, you can get from the second equation, what is U1 prime? Gamma U prime, Ux prime. It is the space component, X component of 4 velocity in the prime frame. On the right hand side, you have U1 to be gamma U Ux minus beta. What is U0? It's the time component of 4 velocity, which is gamma U times C. Again, if I take gamma U outside of this the quantity is inside the bracket, we have gamma U gamma V into Ux minus V. So what is Ux prime? I can divide it by gamma U prime, which you already know. Gamma U prime is gamma U gamma V into 1 minus Ux V by C square. So if you divide this quantity by gamma U prime, gamma U gamma V will get cancelled and you are left with Ux prime equal to Ux minus V by 1 minus Ux V by C square. Similarly, from the third equation, you can write the prime quantity, the y component, gamma U prime Uy prime equal to gamma U Uy. So Uy prime will be gamma U Uy divided by gamma U prime, and gamma U prime is known to you, which is gamma U gamma V into this gamma U, and that gamma U will get cancelled and you get Uy prime equal to Ui y divided by gamma V into 1 minus Ux V by C square. Exactly the same way you can relate the Z component, which is Uz prime equal to Uz by gamma V into 1 minus Ux V by C square. You see the transformation of the three components of 3 velocity looks much complicated. I mean, there are different terms on the numerator and denominator which doesn't match with each other, and things look a bit complex. But if you look at the transformation of this, although these 2 equations are obtained from each other, but again these equations are hiding inside that. Here we are expressing in terms of 3 velocity. Here we are expressing the things in in terms of 4 velocity. You see, this looks much simpler, and that is because when we consider 3 velocity, both the numerator and the denominator transform in a new inertial frame. Space gets contracted, time gets dilated. So when you write velocity equal to dx dt, both the numerator and the denominator, they transform, and it doesn't preserve the character of a 4 vector. So that's why you see, when you separately look at 3 velocity, transformation of 3 velocity, forget about, you can arrive at this equation from other way as well. I have shown it you from 4 vector, but I guess you must have done this velocity transformation in your BSc or somewhere in other course where you have seen this equation, right? Ux prime and Ux, how they are connected. And these equations and these equations, they are content wise same, but you see, if you look at the 4 components of the 4 velocity, they are related with each other in a symmetric manner, and the equations are much simpler. You don't need to remember all these factors here, and that simplicity is because you see here, when you define 4 velocity, you keep the denominator invariant, because you see this is dx mu d tau. So d tau is invariant. Then the transformation, just since space-time 4 vector follows Lorentz transformation, so the 4 velocity is bound to follow Lorentz transformation. Since the quantity in the denominator is invariant, so this and u mu and x mu, they will follow the same transformation. Since x mu follows Lorentz transformation, so u mu will follow Lorentz transformation. So our life is simpler. We can deal with such 4 vectors in relativity with very easy manner. You don't have to be, and the most important thing is the length of the 4 vector is invariant, doesn't change. That has also many useful applications. Okay, I will give you another example here. What is the empowerment? Let me just show you another example here. Okay, before going into the example, I have a couple of things to discuss about. One is what is the length of the flow velocity, or the norm of the flow velocity. You see, we have already got an expression for four vector. What is that expression? That is gamma uc, gamma u ux, gamma u uy, gamma u uz. So if I take the covariant components and take a scalar product u mu, we get gamma u square minus c square equal into c square minus ux square minus uy square minus uz square. Right, so gamma u c square, if you take c square outside, that becomes ex square plus uy square plus uz square equal to u square. So that becomes 1 minus u square by c square, and this is nothing but the Lorentz factor 1 by gamma u square. Remember, this gamma u is the Lorentz factor associated with the velocity of the particle gamma u, right? That is 1 over square root of 1 minus u square by c square. And so you see gamma u square cancels out. So u mu will be c square, and c is a number which is constant in relativity. It cannot change from one frame to other. It's a universal constant, c square. That means the conclusion that that we have inferred earlier for space-time for vector, that c square dt square minus d square equal to invariant. Here you can clearly see that u mu equal to c square, which is a positive quantity, and it remains Lorentz invariant. So length of the pore velocity doesn't change if we go from one frame to other. Okay, and let me show some simple application. Before that, okay, let me tell you, okay, what will be the pore velocity in the rest frame of the particle. In the rest frame of the particle is not moving. So clearly all three components of velocity, will be 0 in that frame. So ux, uy, uz, all of them are 0. And if you put ux, uy, uz equal to 0, that is u equal to 0, the gamma factor, the Lorentz factor associated with velocity u will be 1. Because what is gamma u? 1 over square root of 1 minus u square by c square. U is 0, so gamma u equal to 1. So what will be the pore velocity of the particle in its own rest frame? It will be gamma, which is 1, and then c, and all three special components are 0, so 0, 0, 0. So this is the expression for pore velocity of a particle in its own rest frame. Gamma is 1, c is the time component, and the three space components are 0. Now calculate u mu in this frame. The beauty is that you see here we have no space component, right? No space component. So if I take u mu, you see this is c 0, 0, 0, and c minus 0 is meaningless. Okay, c 0, 0, 0. So you take dot product or scalar product, you get c square again, which is invariant. You see, we have already seen that in a general frame we get u mu equal to c square. In the rest frame we again get c square. Go to any other frame, it will be c square, guaranteed. And that's the advantage of the pore vector formalism. Okay, I am giving you one particular example that how simple things become when you use pore vectors. Okay, so assume there are say two particles A and B which are moving with velocity say u and v in the lab frame. But there is a person who is at rest in the lab frame, and that person is measuring the velocity of two particles A and B, and the velocity of A is u and velocity of B is v. And now if I ask you calculate the Lorentz factor corresponding to the relative velocity between the two particles, right? So first you have to calculate what is the relative velocity between the two particles, then you have to calculate what is 1 over square root of 1 minus that number square by c square. So it will be quite a cumbersome lengthy algebraic exercise. But if you use pore vector formalism, it is very simple and straightforward. One thing which I have not mentioned and I would like to mention here is that not only the scalar product or dot product of a pore vector with itself, but the dot product and scalar product between any two vectors is a Lorentz invariant. So if I have two separate pore vectors, say u mu and v mu, and in one frame I take the product, scalar product u mu v mu, that is u upper mu v lower mu, then it will be same in any other inertial frame, that will be equal to u mu prime and v lower mu prime. So the dot product of any two pore vectors remains same in all inertial frame. Now let us solve this problem using pore vector formalism. So in the lab frame, how do we write pore velocity? So the pore velocity of the particle A will be gamma, I am writing that as u mu, which is equal to gamma u First component is time component c, comma u. U is the velocity of the particle A in the lab frame. And we write the forward velocity of the particle B as v mu, whose components are, you see, in this case the Lorentz factor should be gamma v because the velocity of the particle is v, right? So don't mix up things. Earlier I was using v to denote the relative velocity between the two inertial frames, but it can be anything, whatever you choose. Accordingly you have to write down the equations, right? So because there are only 26 alphabets in English, so if you use them, of course they might be used multiple times, and you have to be careful about the notations. So v mu equal to gamma v. C is the time component, v is the space component of velocity, for velocity. And if I take a dot product or scalar product, u mu, v mu, you see, if I take the this this mu on the lower side, I will have to put a minus sign in the space component, minus v, so gamma u, gamma v, c square minus u dot v. And if I take c square outside, it becomes gamma u, gamma v, c square into 1 minus u dot v by c square. Now I want to relate this quantity with the relative velocity, the gamma factor for the relative velocity. So to do that, let us now jump or switch to the frame of the particle A. If we jump to the frame of the particle A, that's the rest frame of the particle A. And in that frame, if I want to write down the forward velocity of the two particles, how do they come out? So we are switching our frame from the lab frame to the frame of the particle A. And in the frame of particle A, the particle A is not moving, it is at rest. So in that frame, I have just told you a couple of minutes ago that how to write the forward velocity of a particle in its own rest frame. So u mu prime is simply gamma is 1 in that frame, c 0. That's the forward velocity of the particle A in its own rest frame, right? And let us define the velocity of the second particle, that is the particle B in the frame of A as v mu prime. So we are labeling this frame as prime frame, that is the frame A in which the particle A itself is at rest. So that's why u mu prime is c comma 0, and v mu prime is the forward velocity of the particle B in the frame of A. And let us define the velocity to be w or w. Okay, w, that is the relative velocity. Velocity of B with respect to A. That means the velocity measured by A. Velocity of B measured by A. And in that case, v mu prime will be gamma w c comma w. W is the free velocity of the particle B measured by particle A. And if I take a scalar product again of the two forward velocities, u mu prime, v mu prime, v mu lower prime, of course this is 0. You see, and if it is 0 on the first term matters, you see, right, it's gamma and w c square. And I told you that the dot product or scalar product between any two forward vectors is a Lorentz invariant. So I can equate this gamma w, u mu prime, v mu prime with u mu, v mu, which you have calculated earlier in the lab frame. And if you equate these two terms, you can clearly see that c square gets cancelled. So gamma w is gamma u, gamma v into 1 minus u dot v by c square. And it is very simple. If you want to arrive at the same result using an algebraic expression of gamma u, gamma v and calculate w, it will be quite cumbersome and lengthy. The thing is that, you see, I should point out the advantage of using forward velocity. You see, the moment you switch to a frame where the spatial components are 0, the operations become very easy because those spatial components don't have to deal with the spatial components at all. You see, when we took a product of u mu prime, v mu prime, although w is unknown to me, since it is 0, it doesn't matter there. 0 or w gun kore 0 hoye gelo. So only c square gamma w matters, right? So whenever you switch, so we shall see such examples which are called center of momentum frame. When we will discuss about forward momentum, we will come to that. And the goal of switching to center of momentum frame is to jump to a frame, inertial frame, where the total momentum goes to 0. And that makes the things extremely simple, right? And that's the advantage of forward velocity. Okay, how much time we are left with? Okay, we still have time. Fine. So this is the forward velocity. There are many other forward vectors. I will discuss them one by one because we will be needing these quantities for in our further discussion. Okay. Any question up to this? বলো।
হ্যালো,
হ্যাঁ, শুনতে পাচ্ছি, বলো।
কোভেরিয়েন্ট আর কন্টাভেরিয়েন্টের মধ্যে ডিফারেন্সটা কি একটু যদি বলতেন?
হ্যাঁ, সংক্ষেপে বলি, কারণ দেখো মানে এখানে আমাকে তাহলে পিকচুরিয়াল রিপ্রেজেন্টেশন দিয়ে বোঝানোর সুযোগ নেই আমার এখানে। কন্ট্রাভেরিয়েন্ট আর তাহলে দেখো যে কোনো ভেক্টর আমাদের এই তফাৎটা আমরা বুঝতে পারি না ইন কার্টেসিয়ান কোঅর্ডিনেট সিস্টেমে, কারণ কন্ট্রাভেরিয়েন্ট আর কোভেরিয়েন্ট কার্টেসিয়ান সিস্টেমে আলাদা হয় না, দুটো একই। তাই জন্য তফাৎটা আমাদের মাথায় রাখতে হয় না যে কন্ট্রাভেরিয়েন্ট কম্পোনেন্টও যা কোভেরিয়েন্ট কম্পোনেন্টও তাই অর্থোগোনাল কোঅর্ডিনেট সিস্টেমে। কিন্তু যখনই তুমি নন অর্থোগোনাল কোঅর্ডিনেট সিস্টেমে যাবে তখন এটা ট্রু নয়। কারণ কি করা হয়, কন্ট্রাভেরিয়েন্ট কম্পোনেন্ট গুলো হচ্ছে রাফলি স্পিকিং বলছি আমি, কারণ ম্যাথমেটিক্যাল বলতে গেলে তোমাকে অনেক কিছু বলতে হবে, হ্যাঁ, এবং এটা আরো সুবিধা হয়। তোমরা নিশ্চয়ই এটা পড়েছো মেট্রিক টেন্সে যখন পড়ানো হয়েছিল, যখন লোয়ারিং এন্ড আপারিং অফ ইন্ডিসেস নিশ্চয়ই পড়েছিলে, কোনো না কোনো কোর্সে পড়েছো। জি মি নিউ জানা থাকলে কি ওটাকে ইউজ করে কিভাবে তুমি কিভাবে আপার লোয়ার এতে যেতে পারো, যদিও ওটা ম্যাথমেটিক্যাল। ফিজিক্যাল পিকচারটা হচ্ছে এটাই যে তুমি যখন একটা বেসিস থেকে আরেকটা বেসিস যাও, তার মানে কি কোঅর্ডিনেট ট্রান্সফরমেশন মানে কি তুমি বেসিসটা চেঞ্জ করছো, একটা বেসিস থেকে আরেকটা বেসিস যাচ্ছ। এখন বেসিস ভেক্টরগুলো যেভাবে ট্রান্সফর্ম করবে, ভেক্টরের কম্পোনেন্টগুলো সেভাবে ট্রান্সফর্ম নাও করতে পারে। এখন কন্ট্রাভেরিয়েন্ট ক্ষেত্রে সেটাই হয় যে বেসিস ভেক্টর যেভাবে চেঞ্জ করছে আর ভেক্টরের কম্পোনেন্টগুলো যেভাবে চেঞ্জ করছে, সেটা উল্টো। যদি ম্যাট্রিক্স নাও তুমি, এখানে ইনভার্স ম্যাট্রিক্স হয়, মানে বেসিস ভেক্টর যেভাবে চেঞ্জ করছে ওটা তার ইনভার্স হবে। কিন্তু কোভ্যারিয়েন্টের জন্য যেটা হয় যে বেসিস ভেক্টর এন্ড দ্য কম্পোনেন্টস অফ ভেক্টর দে চেঞ্জ ইন আ সিমিলার ওয়ে, দ্য ট্রান্সফরমেশন ম্যাট্রিক্স উইল বি আইডেন্টিক্যাল। এবং এটা কখনই হবে যখন তুমি নন অর্থোগোনাল সিস্টেম ইউজ করবে, তখনই এই ডিফারেন্স তুমি বুঝতে পারবে যে কোভ্যারিয়েন্ট কম্পোনেন্টস এন্ড কন্ট্রাভেরিয়েন্ট কম্পোনেন্টস আর নট সেম, বিকজ ইন ওয়ান কেস ইউ আর টেকিং দিস পারপেন্ডিকুলার কম্পোনেন্ট, যেটা আমরা আগে ছবিকে দেখছিলাম না, যে অর্থোগোনাল হবে যে একটা পারপেন্ডিকুলার ড্রপ করছি, পারপেন্ডিকুলার ঠিক নয়, মানে একটা প্যারালাল লাইন টানছি যেটা প্যারালাল টু দ্য আদার অ্যাক্সিস, এবং সেটা যেখানে কাট করছে সেটাকে আমি বলছি ইউজুয়াল কন্ট্রাভেরিয়েন্ট কম্পোনেন্ট। যখনই তুমি নন অর্থোগোনাল সিস্টেমে চলে যাবে তখন তোমার এই কম্পোনেন্ট গুলো, তখন তোমাকে ওই লাইনের প্যারালাল আঁকতে গেলে সেগুলো আলাদা হবে, রাইট? সো অর্থোগোনাল থেকে নন অর্থোগোনালে গেলে তোমার কম্পোনেন্ট গুলো পাল্টে যাবে, কন্ট্রাভেরিয়েন্ট কোভ্যারিয়েন্ট কম্পোনেন্ট গুলো, যেটা কিনা কার্টেসিয়ান কোঅর্ডিনেটে কোনোভাবে তুমি বুঝতে পারবে না। এটা সেম, এক্স্যাক্টলি সেম। এখন ম্যাথমেটিক্যালি খুব সিম্পল ভাবে বলা যায় যে তুমি যদি মেট্রিক টেন্সরটা জানো, যেটা কিনা আমরা এখানে মিনকস্কি মেট্রিক, আমি মেট্রিক কথাটা এখনো একবার ইউজ করিনি। তার মানে হোয়াট ইজ মেট্রিক? ওকে, মেট্রিক ইজ বেসিক্যালি গিভিং ইউ দ্য শর্টেস্ট ডিস্টেন্স বিটুইন এনি টু পয়েন্টস ইন আ manifold. So here our space-time manifold is 4-dimensional. We have 3 space coordinate, 1 time coordinate. So we are labeling each point as an event and using 4 numbers attached to each event. And when you calculate the distance between the two events in Euclidean geometry, you use your b square plus dy square plus dz square. In case of 4 dimension, we use c square dt square minus d square minus dy square minus dz square. So that's a difference in geometry of the space time. And so in Euclidean geometry, you use a plus sign, here you use a minus sign. So visualization is not always simple. It depends on the geometry. So what is the metric here? G mu nu. We have the plus for time 1, minus 1, minus 1, minus 1, and there is no harm in choosing other signature. Some people prefer to use minus 1, plus 1, plus 1, plus 1. Ultimately, you will get same things. I mean, only the notations could be different, but the final result will be same. So it's up to people's choice how do they choose the notations. But once you choose your metric, it is easy to go from upper to lower by uppering or lowering indices by one from the other. So contravariant, covariant. Once you define a contravariant, you can get the covariant components by simply using the metric tensor. Right? So I will come to those things. I have not yet discussed about. ওকে, তোমরা এটা একটু দেখে নিও, তোমাদের ম্যাথমেটিক্যাল ফিজিক্স অনেক কোর্সেই নিশ্চয়ই এগুলো অনেকবার ইউজ হয়েছে, হ্যাঁ কি না? তোমরা কি কখনো কন্ট্রাভেরিয়েন্ট কোভ্যারিয়েন্ট টার্মটা শোনোনি? নিশ্চয়ই শুনেছো। না শুনলে বলো।
আগে হয়েছে।
হ্যাঁ, কারণ এটা তোমাদের মোস্ট লাগি ক্লাসিক্যাল মেকানিক্স, ম্যাথমেটিক্যাল ফিজিক্স অনেক জায়গাতেই হয়তো এগুলো ইউজ হয়েছে। এনিওয়ে, না জানা থাকলে কোনো হার নেই, আমরা যেটা জানা নেই শিখে নেবে, ঠিক আছে? তো আমরা এটা আমি আবার পরে আলোচনা করবো। আপাতত তোমাকে এটা বললাম সেটাই যে বেসিস ভেক্টর গুলো, মানে তুমি যদি বেসিক ডিফারেন্স জানতে চাও যে বেসিস ভেক্টর গুলো আর ভেক্টরের কম্পোনেন্ট গুলো একইভাবে ট্রান্সফর্ম করে নাকি উল্টো ভাবে ট্রান্সফর্ম করে, সেটাই ডিফাইন করে যে কোনটা কোভ্যারিয়েন্ট আর কোনটা কোভ্যারিয়েন্ট নামে বুঝতে কোভ্যারিয়েন্ট একইভাবে ভ্যারি করছে, কন্ট্রা মানে কন্ট্রাডিকশন আছে, দুটো আলাদাভাবে ভ্যারি করছে, নামটার মধ্যে লুকিয়ে আছে ওরা। তো বেসিস ভেক্টর আর ভেক্টরের কম্পোনেন্ট গুলো কিভাবে ট্রান্সফর্ম করে তার উপর ডিপেন্ড করেই আমাকে কন্ট্রাভেরিয়েন্ট আর কোভ্যারিয়েন্ট ভাবে লেবেল করি, এবং তার কম্পোনেন্ট কিভাবে ট্রান্সফরমেশন হয় তারও ওয়েল ডিফাইন্ড ল আছে, যে কন্ট্রাভেরিয়েন্ট কম্পাউন্ডস কিভাবে ট্রান্সফর্ম করে, কোভ্যারিয়েন্ট কিভাবে ট্রান্সফর্ম করে, এগুলো তোমরা হয়তো ইউজও করেছো আগে। জিআর পড়তে গেলে আর প্রথমেই পড়তে হবে, এগুলো না পড়লে পড়া যাবে না, রাইট? সো যেহেতু ক্লাসিক্যাল মেকানিক্স করেছো, জিআর পড়েছো একটু, সুতরাং এগুলো তোমার কাছে ফ্যামিলিয়ার হওয়া উচিত টার্মগুলো। তো আমি এটাতে পরে আবার ফিরে আসবো। ফর দ্য টাইম বিং ইউ জাস্ট অ্যাকসেপ্ট দ্যাট to know the আমরা যেহেতু +1 -1 -1 -1 সিগনেচার ইউজ করেছি, সুতরাং আমরা যদি কন্ট্রাভেরিয়েন্টটা ডিফাইন করে দিই, কোভেরিয়েন্ট অটোমেটিক্যালি ডিফাইন, রাইট? ওকে, এনি আদার কোশ্চেন? Okay, if not, let us proceed further. Now we shall define 4 momentum. So how momentum is defined in Newtonian mechanics? You see, these are interesting quantity, right? You define something called velocity times mass. It's a new quantity called momentum. I don't know whether you have ever pondered about these things. মানে মাস একটা স্কেলার কোয়ান্টিটি, তার সঙ্গে একটা ভেক্টর গুণ করলাম, ইউ হয়ে গেল একটা নতুন জিনিস মোমেন্টাম। সেটা ভেক্টর ঠিকই আছে, কিন্তু তার যে প্রপার্টি গুলো, তাহলে যদি আমার ভেলোসিটি হয় মাস গুণ করছি, তাহলে মোমেন্টাম ডিফাইন করার দরকার ঠিকই আছে। কেন ডিফাইন করি আমরা মোমেন্টাম, রাইট? সো এনিওয়ে, দিস আর ডিপার কোয়েশ্চেন which I am not going to discuss right now. Let us discuss about 4 momentum. So momentum and 4 momentum, 3 momentum, 4 momentum, how are they different? Since we have already defined something called 4 velocity, we can define something called 4 momentum. আচ্ছা, একটা জিনিস বলতে ভুলে গেছি। আচ্ছা, যেহেতু কেউ আমাকে প্রশ্ন করছিল যে স্পিড বাড়াতে 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 লাইটের স্পিডে চলে গেলে স্পেস টাইম অ্যাক্সেসটা কিভাবে চেঞ্জ করবে, তো এখানে আমার তাহলে এটা তোমাদের হয়তো ন্যাচারাল কোশ্চেন হতে পারে যে হোয়াট ইজ দ্য 4 ভেলোসিটি অফ লাইট? What is the 4 velocity of light? How do I define it? Can I write an expression for 4 velocity of light? What do you think? Any guess? Okay, let me show you the definition here. So this is the definition of 4 velocity. U mu equal to gamma u c, gamma u ux, gamma u uy, gamma u uz. Now if I ask you what is the 4 velocity of light?
সবগুলোই সি হবে।
সবগুলোই সি হবে বলছো। এনি আদার অ্যান্সার? এনি আদার অ্যান্সার? আচ্ছা, সবগুলো সি হবে না। আচ্ছা, কেন হবে না সেটা আমার বলা উচিত এখানে।
না, সব সি হবে না স্যার।
কি হবে হলো?
আমার সব সি হলে সি এক্স কম্পোনেন্ট, ওয়াই কম্পোনেন্ট, জেড কম্পোনেন্ট তিনটেরই যদি সি ভেলোসিটি হয়, তাহলে তাদের মানে নেট ভেলোসিটিটা সি এর থেকে বেশি হয়ে যাবে, সেই জন্য।
আচ্ছা, তাহলে কি হবে বলো?
এমন কিছু হতে হবে যাতে নেট ভেলোসিটিটা সি এর বেশি না হয়।
তাহলে কি হবে?
তার মানে স্যার যে কোনো একটা সি, বাকিগুলো জিরো।
তোমরাই বলো কি গেস, জাস্ট মানে জানতে হবে কোনো ব্যাপার না, ভাই গেস করো না, কি ভুল হবে ম্যাসি, কি বলো না কি আছে ভুল
হতে পারে স্যার যে কোনো একটা সি।
আচ্ছা আচ্ছা আচ্ছা, অবশ্যই বলছো ফার্স্টটা সি হবে আর সব বাকিগুলো জিরো হবে। এনি আদার আনসার? আচ্ছা, কোনো আনসার নেই, ঠিক আছে। তাহলে যেটা হবে দেখো যে ইউ আর ট্রাইং টু ডিফাইন দ্য 4 ভেলোসিটি অফ লাইট, and here when you set the definition, remember the definition clearly, then only you can answer this question. How is the definition was set? You see, dx mu was the infinitesimal space time interval in the lab frame, and d tau was the proper time in the particles frame or whatever. Now, can you define the rest frame of light or photon? As I just repeated couple of times earlier, that you cannot define the rest frame for a photon or light. There is no such things, right? Everything is based on light, right? So you cannot define the rest frame for light and calculate d tau. D tau is proper time, and proper time can be only measured in the rest frame of the particle. So suppose you consider photon to be a particle, there is no harm in it, but can you find a photon at rest? Yes or no? No. That means 4 velocity of photon is undefined. You cannot define 4 velocity of a photon because everything is based on the property of light here, because d tau is the proper time interval, right? Since there is no rest frame of a photon, you cannot define the 4 velocity of a photon. The funny thing is that you can define the 4 momentum of a photon. Let us see how, although these things may be a bit contradictory, but okay, I'll clarify things. The 4 velocity of a photon is undefined. What about the 4 momentum of a particle? First, I will discuss about a particle, and then I will talk about photon. Okay, what is 4 momentum? So 4 momentum, again, you see, I already told you, to be a valid 4 vector, it must obey Lorentz transformation. So 4 velocity you have constructed in such a way that it obeys Lorentz transformation. So we don't have any problem with 4 velocity. If we go from one inertial frame to other, we can easily relate the components. So the 4 momentum is simply multiplied by using a scalar m0 to be the rest mass of the particle. So m0 times u mu, and you know the mass is something which is not constant in relativity. If you gradually increase the speed of a particle, its mass increases, and when the v tends to c, it can go up to infinity. That is already known to you from relativity, which I have not discussed in this course. Well, so if you define p mu is the 4 momentum equal to m0 times u mu, you see m0, what is u mu? It's a 4 velocity. And how you defined 4 velocity? It is gamma u into c comma ux comma uy comma uz, which is nothing but u vector. So 4 momentum is m0 gamma u c into u. Okay, let us take m0 gamma u inside. So what is gamma u? It's the Lorentz factor associated with velocity u. So I am writing the terms explicitly. So m0 c gamma u is nothing but 1 over square root of 1 minus u square by c square. And what are the special component? Of course, you can write ux, uy, uz. I have combined them together to write m0 times u divided by square root of this quantity, which is nothing but gamma u. So this is the time component, and these three are space component. Now let us understand the physical significance of the different components. So what is P0? You see, P0 is m0c divided by square root of 1 minus u square by c square. So of course you can tend to see, but usually in real life you see all the times u is much lesser than c. Of course you don't need to take this approximation all the time, but here I'm just showing you the physical meaning of what it says. So m0c, and then if uic is a number which is smaller than 1, if you square it, expand it in Taylor series, you will get 1 plus half of u square by c square. And if you multiply m0c with the terms inside the bracket, you get m0c plus half of m0 u square by c. And if you multiply the time component of 4 momentum with c, what do you get? Look at this. So I am multiplying the time component p0 of 4 momentum with constant number c. And if I do that, you see on the right hand side we have m0 c square plus half of m0 u square. m0 c square is nothing but the rest mass energy of the particle, and half of m0 u square is the kinetic energy. Of course, this is non-relativistic. I can take the relativistic term as well. So this is just to give you a physical interpretation of the first term. If you multiply the time component of 4 momentum with c, that gives you the energy of the particle, total energy, rest mass energy plus kinetic energy. That's the total energy that we have already seen here also. Okay, anyway, since it is multiplied, so here we are multiplying by c. So of course m0 c square, even without doing these things, you can get this meaning clear, because m0 multiplying a c with this term makes it m0 c square by this. So m0 into this is m0 gamma c square. That's nothing but the total energy. So I'm just I have expressed this in another language, the same thing. So P0, the time component of the 4 momentum, is nothing but energy of the particle divided by c. That's the time component of 4 momentum. So P mu, and what is Px, Py, Pz? You can clearly see m0 divided by this is nothing but m0 times gamma, right? m0 gamma u. m0 gamma, why m0 gamma? Because the mass is not a constant, it's a variable. As you increase the speed, this mass will increase. So it's the momentum of the particle, 3 momentum, right? Mass time velocity is the 3 momentum. So m0 gamma u, m0 gamma in relativity, in Newtonian mechanics, is simply write m into u, m0 into u, because m0 is a constant there. So this is the 3 momentum, 3 component of the spatial momentum. Px, Py, Pz constitutes the spatial part of the 4 vector 4 momentum, and E by c is the time component of the 4 momentum. And in a very similar way, if you will calculate the length of the 4 momentum vector, then P, you have to calculate the scalar product P mu, which is nothing but E square by c square minus P square. which is E square minus P square C square by C square, and E square P square E square minus P square by C square. This is already, you must have learned this in relativity, is mg square C to the power 4 divided by C square in the denominator. So 1 C square gets cancelled, and what you get is m0 square C square. Now you see, rest mass is constant, it's invariant. M0 doesn't change. The mass of a particle in its own rest frame is something which is constant. Right? If you go another frame, go to another frame, then it may change, but it is constant in its own rest frame. And C is of course a constant in relativity. So m0 square C square is a Lorentz invariant quantity. So length of a 4 vector, any 4 vector, is the mass of the particle square times the speed of light square. And interesting thing is that whichever frame you go, this doesn't change. And this provides you enormous advantage, because then you can choose your own frame where the calculations are easier. Why should you choose a frame where things are complicated? You can choose your frame so that the calculations are a bit simpler, like the center of momentum frame that I mentioned earlier, where the spatial momentums are 0. If the spatial momentums are 0, then light is very simple. You don't have to multiply all the components with all the components. It's all the time component that matters. Fine. And this has several applications. I mean, if you use 4 momentum instead of 3 momentum, it will make your life much simpler. So you see, it is not a new thing, because when you studied the different things like collision between different particles, or say disintegration of a particle into multiple particles, or I mean different physical effects in quantum mechanics, like Compton effect, Raman effect, which are nothing but collision between particles. There you used the principle of energy conservation and momentum conservation separately, right? You know that energy should be conserved. It's an isolated system. Energy should be conserved, momentum should be conserved, and those principles can help you to solve those problems. The only difference, but remember, important difference in relativity is that energy and momentum are not separate thing, as you thought earlier. They are the components of a single vector. Because you are looking at time and space separately, and you are treating them as separate entity, you think energy is something different than momentum. But in reality, they are the components of the same 4 vector, which you call 4 momentum. You see, the first component is nothing but energy, and the rest 4 vectors are spatial momentum. So when we will apply the energy momentum conservation, we shall not use energy conservation separately or momentum conservation separately now onwards. Rather than that, we will use the energy momentum 4 vector conservation. That means the norm of the 4 vector is Lorentz invariant. So when we go from one frame to other, we can use that principle to solve our problem. And since it's a 4 vector, it obeys Lorentz transformation. So here I have just illustrated this thing with the B mu invariant. So suppose you have some particle collision A colliding with B, producing 3 different kind of particles or radiations, C plus D plus E. Right. So in such problems, you have earlier used energy conservation and momentum conservation. Right. So we shall now merge these two separate energy conservation and momentum conservation into one conservation, that's called energy momentum conservation. Or rather than that, we should call it the length norm of the 4 vector or the 4 momentum will be Lorentz invariant. Whichever you go, the length of the 4 vector doesn't change, and that's the most empowering thing that you should remember. And it's very similar. You see, once you learn the trick, I mean, it is the same thing you apply again and again. Only one underlying principle. Length of the 4, it's very simple. Length of the 4 vector doesn't change under Lorentz transformation. So that's all that there is, right? So 4 velocity and 4 momentum. Okay, কত সময় আছে আর? আচ্ছা দেখা যাক, একটু আলোচনা করা যেতে পারে। তাহলে 4 ভেলোসিটি আমরা আলোচনা করলাম, 4 মোমেন্টাম আলোচনা করলাম, এবং 4 মোমেন্টাম কিছু অ্যাপ্লিকেশন আলোচনা করা যেতে পারে। আচ্ছা, একটা আলোচনা করি এখানে। So let us discuss about proton antiproton power production. Okay, and we shall solve this problem using this 4 momentum concept. Okay, so let us discuss collision process in the lab frame, where one proton is at rest in the laboratory, another proton is coming from this side and collides with the proton at rest. So let us label those 2 protons as proton A and proton B. right? The mass of proton is known to you. The rest mass energy of the proton is around 938 MeV, that is known to you. And after this collision, suppose the collision produces one new proton and one antiproton. So together we have 3 proton and 1 antiproton, and let us call this whole system as C. C is not speed of light, okay, so don't get confused sometimes because we are using the same kind of notation everywhere. So C is not speed of light. C, I am labeling this whole system to be C, right? In the lab frame we have 4 particles here. Okay, now you want to ask a question, simple question, then what is the threshold energy for this pair production, this proton antiproton pair production? So what is the threshold energy that this proton must have in order to create a proton and new proton and antiproton in the laboratory? So this is one proton, this proton is at rest, they collide and then produce a new proton and antiproton. What should be the threshold energy for this proton antiproton pair production? That is our question, and we want to solve this with 4 momentum concept, which is very easy. So as I told you, conservation of energy momentum in the 4 vector notation ensures that the 4 momentum of the particle A, which is proton A, and proton B, we are just labeling, otherwise you will not be able to distinguish which proton we are talking about. So I have labeled this to be A and this is the B. So P mu A plus P mu B is equal to P mu C, the 4 momentum of this system of particle. And if we calculate the norm of the 4 vector on both sides, we have P mu A, P mu B. Of course, this should be one should be contravariant, other should be covariant. So I have written them separately, and it is a matter of, it could be a matter of confusion. That's why I have used a bracket and put A outside or B outside. It's up to you how do you use different notations. So there is no harm in using different kind of notation, but you should be careful that it should not be confusing. Okay. So on the left hand side you see P mu of A plus P mu of B. That means the norm of the 4 momentum of proton A, norm of the 4 momentum of proton B, plus a mixture of the two, P mu of A into P mu of B equal to P mu C. Now you may wonder why I am writing this to be P mu C. Why I am not writing in a similar fashion, C, D, E, F, and then I could have written them separately and take a product to make my life complicated. I have done this intentionally. Why? Because I know that the length of the 4 momentum is preserved. It doesn't matter which frame you go. So if I go to the center of momentum frame, so on the left hand side I am using the lab frame. On the right hand side, because the square of that quantity, the 4 momentum, that remains a Lorentz invariant. So my calculation becomes much easier if I go to the center of momentum frame. Right. So in that case, the total special momentum adds up to 0. So you don't have to bother about the special part at all. So as if the entire system is at, so you just have to take the time component. And also, you see, each of the proton have mass MP, antiproton has same mass MP. So if you take P mu, since if I add all the masses, MP plus MP plus MP plus MP, it's a 4 MP. So if you take the square of the first term, this is 16 MP square C square. Right? This is the first time component. Only space part is 0, and I am intentionally executing this calculation of the length in the center of momentum frame, because it is not known to me what is the velocity of this particle or that particle or that particle. I can define 4 different variables and make my life complicated. Instead of doing that, I combine them as a system and I go to center of momentum frame. And since I can do that only because the length of 4 momentum doesn't change from one frame to other. Otherwise, it would not have been possible, right? We cannot do that. On the left hand side, you see our life is simple because we know one particle at rest and another particle is bumping on top. So I can define only one velocity for this particle and this at rest. So I know how to write the 4 momentum of a particle at rest. What should be the 4 momentum of a particle at rest? Special parts are 0. And what is the first part? First part is E by C. What is the E? MPC square divided by C. That is MPC. So the 4 momentum of the proton B is MPC. That's the time part, and the special part is 0 because in the lab this proton is at rest. On the other hand, this proton which is moving, let us label the energy of the momentum of that proton to be EA and PA. So I am writing them explicitly here as EA by C is the time component of the 4 momentum of proton A, and PA are the special components of the 4 momentum of proton A. And if I take a product of this 2-4 vector, which is not here, twice into P mu A, P mu B, you see the first two terms are straightforward, because I have already shown you that the square of 4 momentum, if you take a scalar product of 4 momentum in any form, that is bound to be mp square c square or m square c square, where m is the rest mass of the particle. The rest mass of the proton is mp. So whether I calculate p mu in lab frame or any other frame doesn't matter. It will always come out to be mp square c square. That's why I have confidently written is mp square c square. The same manner, since the proton B has the same mass, we have again mp square c square. Plus this term we have to calculate. That's why I have written p mu A and p mu B separately and taken a scalar product of that. So since again this at rest, so space part is 0, this is simply, what is that? 2 p mu A, p mu B. If you take a product, you get 16 mp square c square minus, I have already put this is 16 mp square c square. What is this one? This is EA by C into MPC. CC gets cancelled out, right? So you get twice EA into NP, right? So that is what I am writing here. On the other hand, this 2, if you take this 2 mp square c square on the right hand side, that's what I have done here. 16 mp square c square minus 2 mp square c square is 14 mp square c square. And after that I have put the values of p mu A and p mu B. So that is EA by C into MPC. C and C gets cancelled. So EA equal to 7 MPC square. This is the total energy of the incident proton A in the lab frame. But remember, this is the total energy, which includes the rest mass energy and the kinetic energy both, right? So rest mass energy of the proton is mp square MPC square. That's the rest mass energy, and the rest of the energy within this will be kinetic energy of the proton. So that is MPC square plus kinetic energy. So the threshold energy should be 7 MPC square minus the rest mass energy, which is 6 MPC square. And since we know that the rest mass of energy of a proton is 938 MeV, so if I multiplied 938 with 6, I get 5.628 giga electron volt. So that's the threshold energy required for this collision to take place. That is for producing a proton-antiproton pair. Right. So I have just shown you one example, and this entire discussion is based on the one single fact that the length of a 4 vector is Lorentz invariant quantity. You can choose your frame of reference according to your convenience, and where your calculation becomes easier, that's up to you, right? So I can have many other examples, but again these are repetitive. I mean, once you understand the essential point, you can do it yourself. I have given a couple of other examples which I will not be able to discuss because the time is over. Maybe I can continue my discussion from this point onwards. Any question if you have? If you have any question, you can ask. Can you hear me? Hello?
Yes, sir.
Can you hear me? আচ্ছা, ওকে, ঠিক আছে, ঠিক আছে। কোনো প্রশ্ন থাকলে প্রশ্ন করতে পারো। ঠিক আছে, যদি কোনো প্রশ্ন না থাকে আমি তোমাদের নোটসটা পরে আপলোড করে দেবো। Then you can read it again, and if you have any question, you can also ask later. ঠিক আছে? Okay, ঠিক আছে। Okay, thank you.
Okay.
Okay.